Okay. Good afternoon, everybody. I hope you keep your energy in the last day of the conference. Yeah. So in this session, I would like to start the session by Professor Sinan Balci from the Department of Photonics, Izmir Institute of Technology, Turkey. First of all, I would like to introduce Professor Sinan Balci, graduated from Department of Chemistry, Middle East Technical University in 2000 year, and then master degree from Bilkent University. And he did the PhD program from Max Planck Institute for Solid State Research in Germany. And in Swiss, PhD did in 2006 in the Physics Department of Federal Institute of Technology, EPFL, Switzerland. And after two postdoc, he joined to the Izmir Institute of Technology as assistant professor, and just now he is a professor in Izmir Technical University. His working area is light matter interaction in nanoscale dimension, including plasmonic, excitonic, polariton, and colloidal nanoparticles, and two-dimensional nanomaterials. The title of his talk today is colloidal pexocytic nanoparticles. Professor Sinan Balci, I would like to pass the microphone to you to start your talk.
Thank you very much for the nice invitation. Can you hear me?
Yeah, I'm hearing
okay.
You, and also I can see your screen. But if you share the full screen, it would be appreciated.
Okay, now I think it's clear.
Yeah, it's good.
Good afternoon, everybody. Thank you very much for the nice introduction and invitation. So today I will talk about colloidal plectronic nanoparticles. And I am from Izmir Institute of Technology, Department of Photonics. And so my research group is there. And I will also shortly introduce my research group. So today, mostly I will talk about colloidal plasmonic nanoparticles and colloidal plectronic nanoparticles, and how can we synthesize these nanoparticles, and what is the difference between a plasmonic nanoparticle and plectronic nanoparticle, and we will try to understand the difference between these two particles. And my research group is at Izmir Institute of Technology, Department of Photonics, and so I can divide my research group into two parts. So we are working on 2D nanomaterials and also plasmonics, and today mostly I will talk about plasmonics, so colloidal plasmonic nanoparticles, and we are also synthesizing colloidal semiconducting nanoparticles, for example, perovskites and cadmium selenide nanoparticles, and also other carbon dots, for example. But today I will mostly talk about plasmonic nanoparticles and interaction of these plasmonic nanoparticles with extonic sources, and mainly these are the Frankel extons in J aggregates, and try to understand the interaction between these plasmonic nanoparticles and extonic sources. And so we have also facility for synthesis of 2D nanomaterials, for example, single layer graphene, graphene, and 2D nanomaterials. And we try to understand the optical properties of these 2D nanomaterials. But today I will not talk about these nanomaterials today, but mostly I will talk about the plasmonic nanoparticles and plectronic nanoparticles. So the question is, go to nanoscale dimension, the interaction between light and matter is very interesting in our research group. So we are very interested in the interaction of light with matter. So as a matter part, we have plasmonic nanoparticles, and as a light sources, we have plasmonic nanoparticles. Incoming light interact with the plasmonic nanoparticles. So in conductors, we have plasma frequencies, of course, and when you go to nanoscale, the quantum of plasma oscillations are plasmons. So these are electron oscillations. So when the instant light interact with these plasmons, so we can generate polartons. So these are hybrid particles, half matter and half light properties. And the properties of polartons are very interesting because they show properties of both matter and light. So we can divide the interaction between the light and matter into two parts. So we can call this as strong coupling and weak coupling. So the question is, what is the difference between weak coupling and strong coupling? In the weak coupling regime, the interaction between the light and matter is weak, as the name implies, and we can modify the optical properties of the quantum emitters. For example, we can change the lifetime, for example, of these quantum emitters, and so the Purcell effect and also the spontaneous emission rate of the modified in the weak coupling regime. But if you go to strong coupling regime, there is a huge difference between the strong coupling regime and the weak coupling regime. In the strong coupling regime, the interaction is strong, and there is a reversible energy exchange between light and matter. And so the interaction is very strong here, and you can exchange energy between the quantum emitters and, for example, cavity. This may be a photonic cavity, or in our case, for example, plasmonic particles. So there is a reversible energy exchange between plasmonic sources and also the exotonic sources. And today we will see these plasmonic nanoparticles. These are the polartonic nanoparticles. So they show half plasmonic properties and half exotonic properties. And of course, the interaction between light and matter starts from the plasmonic nanoparticles. So when you take the conductor, for example, thin metal film, in conductors, we have plasma oscillations, and quantum of these plasma oscillations are plasmons. So we have bulk plasmons and also surface plasmons. In the bulk of the metal, we have bulk plasmons. So these are compared to surface plasmons. Surface plasmons are transverse oscillations, and if you compare with the surface plasmons with the bulk plasmons are longitudinal oscillations, and the polarizations are different. So when you send instant light interacts with the surface plasmons, and photons coming from the instant light and surface plasmons on the metal surface. So these are the electron oscillations, interact strongly at certain conditions, of course, not every day. So the interaction is very strong when you satisfy these conditions, and then we can generate this surface plasmon polarton generation. So these are the polartons. They show half electron oscillations and half photon oscillations. And there are many ways of excitation of these surface plasmon polartons. For example, the simplest example is you can take a gold film, for example. On the left-hand side, you see a gold film. So this is a very thick gold film. When you send the visible light, for example, the visible light cannot pass through this gold film because it's very thick optically, and the light cannot be transmitted through this gold film. And when you look at the screen, you see the black screen here because there is no transmission of light. But what happens when you drill some holes in this gold film? So you see this on the right-hand side. So you can see this array of gold holes, nano holes on the gold film. And now instant photons interact strongly with the periodic structure on the surface, and these photons can be converted into surface plasmon polartons. Now the photons interacting with the plasmons, and now polartons can go through these holes, and they go other side of the film. And now if you look at these films in the transmission mode, you can see blue, green, and red figures here, because now light can be transmitted through these nano holes. And so the most important paper about this study is the Ebbesen paper in Nature in 1998. So after this study, the interest in plasmonics increased hugely, and there are many interesting studies. So when you go to down nanoscale regime, so plasmonics is the interaction of light with plasmonic nanoparticles, and you can generate surface plasmon polartons, and now light can be manipulated on the nanoscale regime by generating these plasmonic structures. For example, so in this case, you can also think about colloidal gold nanoparticles. For example, here you see this glass windows here, and they are decorated with gold nanoparticles. And depending on the size of the gold nanoparticles, so we have here interaction of light with these gold nanoparticles. These structures has been known from the 12th century, and but the interest, of course, increased enormously because of the development in the fabrication technology and also synthetic chemistry and also optical investigations. Now we can understand why these structures are colored, and the interaction between the light and these metallic structures are very interesting. So we can synthesize these colloidal plasmonic nanoparticles. So you can start, for example, with silver ions, and then you can reduce them. You can generate seed nanoparticles, and these are silver nanoparticles. They are spherical shaped, but they have resonance frequency around 400 nanometer. But if you want to tune the resonance frequency, you have to change the size. So in our case, we can tune the size of these nanostructures, and we can generate anisotropic structures. In this case, we can generate silver nanoprisms. And depending on the size of the plasmonic nanoparticles, you can change the resonance frequency from 400 nanometer to 1100 nanometer. And now the plasmonic frequency of these structures are tunable depending on the synthetic conditions. So we mostly change the seed nanoparticles in the synthesis procedure. And if you increase the number of seed particles, the size is reduced. And if you decrease the size of the number of seed particles in the synthesis, now we can generate larger particles. Larger particle means larger wavelengths, and you can generate in the infrared regime the plasmonic resonances of these structures. So another thing is people mostly call these structures as plasmonic nanoparticles, as the name implies, of course. So plasmons are quantum of plasma oscillations, and these are the free electron oscillations, right? And when the instant light interacts with the plasmons, so you generate plasmon polartons. And of course, on the surface of the metal, we have surface plasmons. The generated polartons are surface plasmon polartons. When these are localized, we call this as localized surface plasmon polartons. But shortly, people say this as plasmons or plasmonic nanoparticles, but the name sometimes, we should say that these are the localized surface plasmon polarton nanoparticles, or in short, we say this as plasmonic nanoparticles. So by changing the size of the silver nanoprism, for example, you see here by simulation and also by experiment, the size of the particles can be tuned from a few tens of nanometers to 100 nanometer or larger than 100 nanometer. And you can tune the color or resonance frequency of these nanoparticles. And here you see this resonance change from 400 nanometer to 1100 nanometer. So this can be modified by changing the seed nanoparticles in the synthetic procedure. By using, for example, finite difference time domain simulation package, we can also simulate these nanoparticles, and the resonance frequency of these nanoparticles can be tuned by changing the size of these nanoparticles. And today, our main goal is to understand the different nanoparticles and plasmonics. So what is the difference and what are these plasmonic nanoparticles? And here you see plasmonic nanoparticles, the blue colored graph. So we can synthesize these plasmonic nanoparticles. So we call this as nanoprisms. And then as an exotonic source, we use J aggregates. So these are the dye molecules. So they aggregate side by side. And at high concentration, they form a very interesting resonance frequency here. So this is the J band, and they called, so it is called J aggregates. So these are dye molecules. And then when you combine these plasmonic nanoparticles with these dye molecules, they self-assemble on the surface of these nanoprisms. And then they interact strongly. There is a reversible energy exchange between these exotonic sources and plasmonic sources. And in the strong coupling regime, as you see here in the absorption and absorption graph, so there is a deep transparency dip at the resonance frequency. So you can change the resonance frequency of plasmonic nanoparticles, and then you can obtain the dispersion curve. So at the bottom here on the right-hand side, you see this dispersion graph. So the x-axis is the plasmon resonance energy, and the y-axis is the energy So you can tune the plasmonic resonance frequency, and here you see the bare extonic frequency, and also you can see also the bare plasma band. So when they interact strongly, they generate these plasma exton hybrid particles, and then we call these particles as perextonic nanoparticles. And on the right hand side, in the up here, you see a graph of this image of these particles. The red one is the pure J aggregate. So this is bare J aggregate without anything. In the middle, you see the pure plasmonic nanoparticles, number 3. And on the right hand side, you see these purple colored hybrid particles. So these are pure perextonic nanoparticles. There is no uncoupled plasmonic nanoparticles or J-grade dyes. So we synthesize these nanoparticles, and then we remove these dye molecules, uncoupled dye molecules, by centrifugation. And the obtained particles are pure plasma exton hybrid particles, and then we call this as colloidal perextonic nanoparticles. And so these are very interesting, actually. So you generate these particles, and they show half matter and half light properties. And we try to understand the interesting physical properties of these nanoparticles, and they show both properties of plasmonic nanoparticles and also extonic nanoparticles. So we also synthesize other colloidal quantum dots, for example, cadmium selenide, carbon quantum dots, and perovskites. And we can tune the resonance frequency of extonic sources by changing the size of these quantum dots. And in our research group, mainly, we try to combine these plasmonic colloidal nanoparticles with the colloidal semi-conducting colloidal quantum dots. And at the final stage, we would like to obtain hybrid nanoparticles, and we want to obtain this in colloidal form, because when you obtain colloidal form, you can fabricate devices, or you can separate them, and you can coat them on any surface, and you can generate active devices based on the plasmonic and perextonic nanoparticles. And so we are very interested in the colloidal part, because these are applicable. So you can use them in solar cell, for example, light emitting diodes, or other glazing applications, because we have them in large quantities, and we can coat them on a surface, and we can generate different active devices. So we are also trying to generate active devices by using 2D nanomaterials, for example, graphene, single layer and multi-layer graphenes, and try to combine these perextonic nanoparticles with the 2D nanomaterials. So here you see the plasmonic nanoparticles, and we try to add small quantities of J-grade dyes. And you see here the graph, and when you add these dye molecules, they self-assemble on these plasmonic nanoparticles. And if you look at the extinction graph here, now the obtained graph shows half plasmonic and half extonic properties. So when you add small quantities of dye molecules, the interaction is weak between the plasmonic nanoparticles and the extonic sources. And you see here, for example, starting from bare 1, 2, 3, for example, in 1 and 2, there is no splitting. So we call them as weakly coupled here in 1 and 2, because there is no splitting in the energy levels of the plasmonic nanoparticles. But you can increase the number of dye molecules. So because the number of dye molecules, or the number of particles, quantum emitters, very close to plasmonic nanoparticles, if you increase this quantity, you can increase the revised splitting energy, and that's what you see here. And in the strong coupling regime, you see this increase in the revised splitting energy when the dye molecules are very little. So we are in the weak coupling regime. So the rate is very fast in the synthesis. This is electrostatic self-assembly of dye molecules on the plasmonic nanoparticles. So we can also study the optical properties of these nanoparticles at the single nanoparticle level. You see here single perextonic nanoparticle and single plasmonic nanoparticle extinction graph in the dark field imaging. Here we collaborate with a research group in Sweden, and now you see here single nanoparticle perexton extinction graph, and single particle also shows a nice strong coupling of these plasmonic nanoparticles and extonic sources. And we have also fabricated other plasmonic particles, and we combine these with the external sources. For example, we generated nanodiscs and nanorings, and also sharp corners containing nanoparticles. So these are the decadral pentagonal nanoparticles. Here you see these pentagons are very important because they have sharp corners, and we would like to increase this Rabi splitting energy by focusing the electric field at the sharp corners of these nice structures. And another thing is the nanorings. So these nanorings contains the holes in the center of this nanodisc. So we first synthesize seed nanoparticles, and then we synthesize silver nanoprisms. We convert these nanoprisms into nanodiscs, and then we combine these nanoprisms with the nanodisc with the gold ions, and there is a replacement reaction between the silver on the nanodisc and the gold +3, because gold is more noble than the silver. There is a displacement reaction, and so in the center of the nanodisc, so you can see a hole here. These holes are very important because you can confine the electric field at the center. Now, if you can precisely locate the, for example, quantum dots, semiconductor quantum dots, for example, carbon quantum dots or cadmium satellites and other semiconductor quantum dots, we believe that we can increase the light-matter interaction at the center of this nanoring. So we are also working in this direction. So and we hope to get nice results from these nanorings also. And this is the method that we use for the synthesis of nanodiscs and nanorings, and also the interaction of external sources with the JE dyes. So you can also find detailed information in our previous publications. And another thing is the nanodiscs are more stable than the nanoprisms. So this is the main conclusion from one of our previous studies, because when you heat the nanoprisms, so you can convert these structures into disc-shaped nanostructures. They are more stable than the nanoprisms. And when you coat these nanodiscs with the J dyes, and you can obtain very stable plectronic nanoparticles, and you can use them in device application, for example. And so we believe that the nanodiscs are more interesting than the nanoprisms. Are more stable, and the structure is very easy to fabricate. So here you see the change of the morphology of these nanoprisms to nanodisc. So in this case, we perform this experiment in an oil bath experiment, and we convert these triangular-shaped nanoprisms into nanodiscs, and nanodiscs are more stable than the nanoprisms, because here the structure is thermodynamically more stable than the nanoprisms, because the edges of these nanoprisms are truncated, as you see here in the nanodisc, and the fabricated structures are very stable. Here you see again a very nice representation of these colloidal plasmonic and plectronic structures. Here in the first graph, you see this blue graph showing the bare plasmonic nanoprisms and also nanodiscs. And we have a very nice resonance wavelength at around 600 nanometer. And in the middle, you see the JY dyes. So they are in red colored, you see. And these JY dyes, they aggregate side by side. You see small peak here at around 500 nanometers. This is the monomers. So these are the unaggregated dyes in the system. So they also have resonance here at 500 nanometers. So when you decrease the concentration, for example, much slower than the 10⁻⁴ or 5 molar, so you can convert all the JY dyes into monomers, and in this case, you can see only broad resonance peak at around 500 nanometers. But at high concentration, for example, 1 millimolar or close to that one, the dye molecules aggregate, and they form a very sharp peak here. You see here a nice resonance wavelength at around 600 nanometers. And when you combine these external sources with the plasmonic nanoparticles, you can generate these colloidal plectronic nanoparticles. These structures are very interesting, I think, because Now, the interaction between the plasmonic nanoparticles and extonic nanoparticles are strong because we have modification in the energy levels. As you see here, you see this in the extinction graph, and they show half plasmonic and half extonic properties, and we can modify the optical properties of plasmonic nanoparticles. And here you see the change of the color of these colloidal plexonic nanoparticles as a function of dye molecules, and the resonance Rabi splitting energy here is proportional with the square root of the dye concentration, and this is a well-known from the literature also. And when you change the concentration, and the relationship between the Rabi splitting energy and the concentration of dye molecules should be linear with the square root of the dye concentration, and that's what we see also here in this graph. So they fit together nicely, as you see here in this graph. And we can also calculate the Rabi splitting energy, and you can calculate the lower and upper polarton branches. And here you see the green one is the bare exon on the right-hand side. We can obtain the dispersion curve. And as you remember, in the strong coupling regime, these plasmonic nanoparticles and extonic sources interact strongly, and there is a reversible energy exchange between these nanoparticles in colloidal form. So these are not single particles. So these are ensemble measurements. And sometimes in the literature, you see a lot of plexonic nanoparticle studies, and most of them are in single nanoparticle or some collection of particles on a substrate, but we synthesize colloidal plexonic nanoparticles. So that means we can synthesize them in liter quantities and in large amounts in uniform shape and uniform properties. So these are all in ensemble measurements. That means we take the synthesized strongly coupled nanoparticles and obtain the physical properties of these nanoparticles in the ensemble level. So ensemble level means for application, it is very interesting because you can coat them on a substrate, or you can fabricate active devices by combining with the 2D nanomaterials. That's why we are very interested in this colloidal form, not the single nanoparticle properties. And here you see this disc-shaped plasmonic nanoparticles. We can simulate them by using the finite difference time domain simulation, and we can obtain the optical properties of these nanoparticles. And you see here electric field distribution at 560 nanometer, 587, and 612 nanometer. So these are the lower polarton branch and upper polarton branch. And here you see in the middle, you see the transparency dip here. That is the resonance field in the middle, because they are strongly coupled, and there is a reversible energy exchange between upper and lower polarton branches here. And so we can increase the Rabi splitting energy by changing the oscillator strength. So this is the number of dye molecules in the system. So you can find the detailed information about the synthesis. I will not talk about the synthesis of these nanoparticles. So you can find our previous publications, and we have detailed information about this. For example, rings and discs, and also prisms. So here you see the rings, and we can tune the ring size also by changing the gold ions in the system. And by theoretical calculation, we can try to understand the optical properties of these rings. So, for example, if you look at this electric field distribution in the middle around the ring, for example, when the size of the ring is around 6 nanometer, so there is a strong electric field localization. So strong field localization means when you place a matter there, for example, quantum dots or some other external sources, so we expect to have some large electric field enhancements and some modification of the nonlinear optical properties of some materials, and also increase in the light-matter interaction. So we would like to perform these experiments at the single nanoparticle level and try to understand the rings and plasmonic nanorings and the interaction with the other extonic sources, quantum dots, and also other molecules. For example, we can also increase the surface and enhance Raman scattering of molecules or other interesting structures. So here you see the other plasmonic nanoparticles. So we can synthesize these nanoparticles by using lasers. So we use 488 nanometer laser. And so first we generate the seed, and by using the seeds, you can generate nanoprisms. And if you expose to laser light further, you can generate pentagonal-shaped, very nice-shaped plasmonic nanoparticles. So these pentagonal-shaped nanoparticles are also very interesting. They are star-shaped. You see here, they have sharp corners, and we can also and nanoparticles. They are very interesting because these sharp corners contain high electric field localization, and we would like to obtain large electric field enhancement at the corners of these decahedron-shaped pentagonal plasmonic nanoparticles. Okay, with this, I would like to finish my presentation. So I explained to you the strong coupling regime. So plasma exon mixed colloidal plexonic nanoparticles, and we can fabricate colloidal nanoprisms, nanodisc, nanorings, and also pentagonal-shaped nanoparticles. And we can generate them in large quantities. That's very important in colloidal form, because when you have this in colloidal form, you can coat them on a surface, and then you can fabricate active devices. And we are mostly working on this colloidal-shaped, colloidal plasmonic and plexonic nanoparticles, and we would like to combine them with the 2D nanomaterials, for example, graphene and multi-graphene also, and other molybdenum disulfide and tungsten disulfide, these other 2D nanomaterials, and we would like to generate active nanophotonic devices out of these colloidal nanoparticles and 2D nanomaterials. So today, mostly I talk about the colloidal plexonic nanoparticles because this is the half of the lab works on these colloidal plexonic nanoparticles, and other half of the lab works on the CVD synthesis of these 2D nanomaterials and device fabrication out of these 2D nanomaterials. Okay, thank you very much for the listening. So do you have any question?
Yeah, thank you very much, Professor Balji, for your nice presentation. I don't see anything in chat bar, but if you have any questions, you can raise your hands. Raising hand also welcome. We have time for a couple of short questions. Yeah. So I have a question, Professor Balji. It was very interesting review, but with examples both in experimental and theoretical works about quantum size effect in different nanoparticle nanostructures, metallic, semiconductors, and so on. The question is that what is the theory of the plasmonic? You mix the plasmonic and, as I understand, plasmonic and excitonic nanostructures together. And I remember that the theory of the excitonic nanostructures comes from the, there are some examples, comes from the quantum confinement effect, and it is an example of the particle in box. The simple explanation is effective mass theory. But plasmonic nanostructures, the theory of plasmonic nanostructures comes from the electromagnetic theory. How we can mix these two theories together to create a suitable theory for your introduced nanostructures? Yeah.
Okay. Thank you very much for the nice question. So first, starting with the plasmonic nanoparticles. So when you take a metal surface, for example, so in metals, of course, we have free electrons. So they oscillate collectively, and these oscillations are plasma oscillations, right? And then quantum of plasma oscillations are plasmons. It's like quantum of light is photon, right? And these plasmons, and they interact with light in certain condition, for example. So when you take a flat silver film, for example, or metal film, on the surface we have surface plasmons, but in the bulk we have bulk plasmons. These surface plasmons, they are actually electron oscillations. There is no light. Okay, so these are electron oscillations. Mm-hmm. So when you combine light with these surface plasmons. So for example, you can use Crashman compression or other gratings, for example. You can use these structures to excite these surface plasmons. So when the light interacts with the surface plasmons, you can generate surface plasmon polariton. So these are the hybrid particles, so half electron oscillations and half light. So maybe first we need to understand the plasmons, and people call these plasmons, but actually this is surface plasmon polaritons, because plasmons are actually electron oscillations in a conductor, quantum of plasma oscillations. So so when you look at the colloidal quantum dots, of course, so you can excite the surface plasmon polaritons in free space. So you don't need to use Crashman cooperation or grating structures. So instant light can couple with the surface plasmons on the metal surface. And when you change the size of the plasmonic nanoparticles, of course, because of the quantum confinement effect, so you can also change the resonance frequency of plasma oscillations, surface plasmon oscillation. And this is, so here, plasmonic nanoparticles that we call is actually surface plasmon polaritons. So when you take colloidal plasmonic nanoparticles, this is localized surface plasmon polaritons on a colloidal plasmonic nanoparticles. When you go to semi-conducting parts, for example, and in that cases, we try to combine them in a fine interference time domain simulation package that we use. So we take a metal surface, and then we assume that the extonic sources are harmonic oscillators. So we assume that the extonic sources that we use, for example, J-grade dyes and also semiconducting quantum dots, so these are harmonic oscillators. And then we change the resonance frequency and oscillation strength and the dielectric condition. And then we coat the metal surface with these harmonic oscillators. And then we try to simulate them here, for example, here in this simulation, right? So we take plasmonic nanoparticles and we coat them with a harmonic oscillator, and we change the harmonic oscillator strength. That means harmonic oscillator strength is the concentration of dye molecules in the system, right? And the Rabi splitting energy, that's the interaction between the plasmonic nanoparticles and the exonic sources, linearly increases with the oscillator strength of the harmonic oscillator. Mm-hmm. And so the plasmonic part, the metallic part, and also exonic part are huge, and because of the quantum confined effect, for example, you can also use colloidal quantum dots, because when you change the size, because of the quantum confined effect, you change the resonance frequency of exonic sources, and you can combine them now in these pre-exonic nanoparticles, and they show half metallic properties and half exonic properties. Mm-hmm. And I think the field is very large here. I think we should discuss more, but I think we don't have enough time. Yeah. Starting from the very simple theory to combination of these plasmonic nanoparticles and exonic quantum dots, we should combine them in a single unit.
Okay, thank you very much, Professor Balci. A short question in the continue. I would like to know about the experiment just now. By absorption spectroscopy, we can detect the plasmonic oscillation and also excitonic. Are there any examples to overlap both of these effects? And if yes, how we can separate these type of oscillation in experiment?
In experiment, we have plasmonic nanoparticles. So they scatter light and they also absorb. So we call this extinction, right? So we have absorption and scattering, and collectively we have extinction spectrum here. And when you combine these nanoparticles with extonic sources, they interact strongly. And all the plasmonic nanoparticles, they interact strongly. And for example, here, maybe you can see clearly. So on the left-hand side, you see plasmonic nanoparticles. They are pure plasmonic nanoparticles. They are all bare plasmonic nanoparticles, so nanodisk-shaped nanoparticles. And in the middle, you see the exonic sources. So these are aggregated dye molecules. So when you combine them here on the right-hand side, you see all coupled, strongly coupled plasmonic and exonic sources here. So when you have an uncoupled plasmonic or exonic dye molecules here, in this spectrum, you see increase in the resonance at around 600 nanometers. So this is pure pre-extonic nanoparticles, strongly coupled plasmonic and extonic nanoparticles, and there is no uncoupled dimolecules in the system and uncoupled plasmonic nanoparticles. So it is pure pre-extonic nanoparticles. We are for sure. So when you look at these nanoparticles at the single level, so this is also one study that we have collaborated with the Sweden group here. So they have taken from this colloidal suspension and they have looked at the optical properties of these nanoparticles at the single particle level. And you see here, the optical properties of the nanoparticle, this pre-extonic nanoparticle, is also the same at the single nanoparticle level. So when you have the uncoupled, for example, plasmonic nanoparticles, you see here another graph here. So this is bare plasmonic nanoparticle. So it is completely different from the pre-extonic nanoparticle.
Thank you very much again, Professor Balci, for your extended answer and clear answer. And thank you again for your coming. Just now, I would like to inform all of you for the closing ceremony at the end of this conference today. It's announced at the program schedule you can find from the website. The first speaker in this session is Hasan Oğuz. I see you, Hasan. Hasan is from the Pamukkale University, Denizli. Can you share, please, your slides?
Of course.
Yeah, I have your voice and also your slides are excellent. You can start, Hasan.
Hello, my name is Hasan Oğuz. I'm going to present our study on low symmetry photonic crystal cavity phase properties. Today, I'm going to start with our simple introduction, then symmetry in photonic crystal, what it's mean, and couplet mode theory, then low symmetry photonic crystal cavity, which we are studying, and our conclusion and future plans. Our focus is to investigate phase properties of photonic crystals, cavity structures. Our goal is to design devices like Mach-Zener interferometer, refraction-based sensor structures, or phase matchers by using phase properties. We try to achieve our goal by using low symmetry photonic crystals. For this study, these photonic crystal structures have slow light characteristic. We use as method, in general, finite difference time domain for calculating quality factors and resonant frequency of our structures. Then we apply couplet mode theory semi-analytically for our calculations. Okay, photonic crystals are, by definition, they are crystals, so they have symmetry. They have three main symmetry. One is translational symmetry, which is A1 and A2. It's square-based pointer. 1 second. Which is this and that, and we have and we have mirror symmetries like this axis and this axis, and most importantly, we have cyclic symmetries, which we are using in our study. When we take a primitive cell of photonic crystal structure into the square lattice, this has infinite symmetry, because when I turn it, it doesn't matter how many turns I turn it, it's still a round shape. But when I add an auxiliary rod like this, when I add an auxiliary rod like this, I need to make a full turn for returning to its original picture. When I add two auxiliary rods, I need a half turn for returning its original picture, etc. So when I put an auxiliary rod, I reduce our rotational symmetry. I use couplet mode theory. When I mean couplet mode theory is a perturbational approach for analyzing the coupling of vibrational systems. This system can be mechanical, optical, electrical, whatever. There must be a vibration, and I can analyze it in space or in time. Couplet mode theory allows a wide range of devices and systems to be modeled as one or more couplet resonators, like this system. For instance, there is a waveguide, then we have a cavity, and there is another waveguide. This is a standing wave cavity, so we call them S2. Energy exists in this cavity in two forms. Localized resonance modes in this cavity and traveling waveguide modes in that 1 and 2 waveguides. For couplet mode theory, I can use couplet mode theory, there must be weak coupling between modes. So our Q factor, quality factor, need to be greater than 13. This system need to be linear, but I can use it in, for instance, curve-type nonlinear systems with some modifications, and also need to be time invariant. Temporal couplet mode equations, the time-dependent equations for a system like this is for that amplitude. This is the overall amplitude. This amplitude carries both phase information and also the magnitude of the electromagnetic wave information is like this. And the waveguide modes can be written as 1B equation. Then I can get the transmission information, and also I can calculate the S parameters from that transform the transmission information, transmission equation. Or omega 0 is our resonant frequency, which that cavity has, and tau is our decay time. When I generalize that equations for using quality factors, this Q instinct mean the quality factor of the cavity, and QW is waveguide quality factor, kind of coupling quality factor. And then I can get the phase information from it with that formula, and also I can get the transmission information and decay time of the resonant frequency. So it's can effectively use analyzing a system. We took our basis on the ultra slow light system studied by Hamza Kurt and Kadir Üstün. This is a site merged couplet cavity and has slow light characteristics. But for the start, we start with single cavity. Then in our future plan, we plan to merge them and make that calculations according to them. For low symmetry modification, I add a auxiliary rod at lambda equal 0.5. A is my primitive cell size, so I put a auxiliary rod for start, and then I start to rotate that auxiliary rod at 0, 30, 45, 60, and 90 degree angles. My rod size in the structure is 0.2 A. For the cavity, it's 0.35 A, and for the auxiliary rod, which I put, is 0.1 A. Ready. This is a square lattice, by the way. Okay, when I calculate the optical properties for non-auxiliary rod, the base structure, I get S parameters of single cavity with couplet mode theory like this. I have a resonant frequency around 0.245, and we have a transmission like that. Then I can get the phase information like this, and my group delay is around minus 52, around minus 52. All are calculated via couplet mode theory. When I put auxiliary rod at 90 degree angle, I get a slight increase in transmission, and slight shift of resonant frequency. And also there is slight shift of phase and a great change in group delay. Change of optical properties of auxiliary rod angle according to for comparison without auxiliary rod system, our resonant frequency make slight deviations, but its maximum deviation is at 45 degree, which we don't want. We want a flat frequency, no change at resonant frequency for designing sake. So we need to optimize this structure when merging, so we stay at the intended resonant frequency. Also, there is a change in full width half maximum. So actually, this give a kind of transmission quality. We don't want to increase or decrease any great fluctuations in it. This biggest fluctuation is at 30 degree. When we look at group delay, we can see some change. We can use for slight variation. We can use for fine tuning when we couple that structure, so we can get needed group delay response. Greatest maximum group delay change is at 30 degree. And also our group delays with auxiliary rod is lower than the okay, they are minus, but actually they are lower than the without rod structure. When we look at the phase shift, our maximum phase shift can be seen at 30 degree, and highest fluctuation at 40 degree, but we have some room to fine tuning of phase shift. And also this small variations, small changes can be used to design necessary phase shifts when we couple that structures. Okay, first we added auxiliary rods, or conclusion and future plans is like, we added the auxiliary rods and reduced the rotational symmetry. And we saw phase shift and group delays can be arranged delicately. It can be fine-tuned by changing the angles of the auxiliary rods. Also, we plan to make necessary calculations with other structure parameter change. Auxiliary rod can be make smaller or bigger, can put away or close to our cavity, etc. We're going to investigate that effects too. We also realized that the change of auxiliary rod angles give rise to modification in resonance frequency and full width half maximum. They are fluctuations, but these fluctuations can change, affect frequency response, and we need to make optimization for get rid of that big fluctuations. So we need some optimization in the future. Our future plan is to calculating of the merged cavity responses and optimizing structure properties for minimal impact on resonant characteristics. Thank you for your attention. Thank you.
So thank you very much, Hassan. Any question, please? There is no question in chat bar. You can ask the question by raising your hand if you have any question. I think there is no question. I thank you again. And without wasting time, I would like to switch the next speaker.
Okay, thank you.
Parisa Soleimani, the next speaker from Tabriz University. Can you hear me, Parisa?
Hello.
Yeah. So, okay. Parisa will talk about the study of diffraction polarization of fork grating printed on die-doped liquid crystal cells. You can share your slides. I have your voice and also.
Hello, are you hear me?
Yeah, I'm hearing you. You can start.
Okay, thanks. Hello, everybody and participant in the name of God. The subject of my article is the study of diffraction polarization of fork grating printed on die-doped liquid crystal cell. My name is Parisa Soleimani and from University of Tabriz Research Institute for Applied Physics and Astronomy. And my co-workers are Dr. Habib Khoshsima from Faculty of Physics, University of Tabriz, Iran, and Dr. Muhammad Yekane from Department of Physics, Institute for Advanced Studies in Basic Science. First of all, I want to introduce a liquid crystal. What is liquid crystal? Is it a state of matter? All of us know common states of matter are solid, liquid, gas, and plasma. But matter can exist in other states other than it. Okay, what is liquid crystal state? Is it liquid, is it crystal, or mixture of liquid and crystals? Liquid crystal is a state that occurs between a solid and liquid. It poses properties characteristic of both liquids and crystalline solids. also possess properties not found in either liquids or solids, may respond to external perturbation, some change with temperature. Okay, here we can show a picture of crystal, liquid crystal and liquid. In some special materials, liquid crystal is shown in a special range of temperature. When heated a crystal in temperature, we can show the characteristic of material is changed. And the characteristic of material is between crystal and liquids. And after the temperature, the liquid crystal changed to liquids. In fact, it is be to liquids. After that, here in this article, we use dyed up liquid crystal. We used E7 liquid crystals, which is a combination of 5 CB, 7 CB, 8 OCB, and 5 CT. And our dye is metal red, which is dye pigments. Here we use for absorbance sense because dye pigments, when the incident beam and pigments, the pigments can change from trans shape to cis shape. In fact, the metal red or other metal pigments, when absorbance special range of wavelengths, it could change the direction of the mucus, and here we use this feature of the dye pigments. Here we saw the liquid crystal cells, two kinds of liquid crystal cells shown. One is planar and second is vertical. In planar, the liquid crystal alignment is parallel to the surface alignment, and in the second is vertical to the surface. But here in this article, we use this feature of liquid crystal cells. And here, when we dubbed a dye by liquid crystal, and after that we incident a laser beam onto it, the liquid crystal could reorient, and they stay vertical to the surface of liquid crystal, and we use this feature of these liquids. After liquid crystal and dyed up liquid crystal, we want to produce fork grating. What is fork grating? Is a common grating, or it has some special features? Fork grating is a special grating, grating state with centric dislocations. In fact, when as you see here the dislocations of fork grating. And when the Gaussian beam in the incident and the fork grating, the emitted light is diffracted. And the main difference between this grating by other is that here just the zeroth order of diffraction is Gaussian, and minus plus the first, minus plus the second, and so on is larger Gaussian phase shape, or is a vortex beam. And the function transmission of the fork grating equation is like that. A and B is a constant, M is topological charge, and theta is also angular. And at the experimental, we use a fork creating mask and dyed up to 2% dyed up liquid crystal cell. The metal red pigments absorption is the range of 532 nanometer, and after that, because of this, we use laser by this wavelengths. This is a setup which is we use in our laboratory. First, we collimate the laser beam by 5 centimeter and 10 centimeter convex laser. After that, we put a diaphragm. After that, we put a polarizer. Our polarizer must be parallel to the alignment surface of the liquid crystal, because in that state the absorption of dye pigments is in the highest level, and we do it and we after that our cell is produced, and here you can see the printed lithography mask on the cell, and it is recorded by CAM. The second picture is recorded by a microscope, and this picture is due by 1% metal red, and the remaining is liquid crystal. This picture is made of 2% of dimetal red, and is recorded by microscope. After printed fork creating mask and what dyed up liquid crystal cell, we put it in front of helium neon laser, and I want to describe it. Helium neon laser, which is a laser we used here, a helium neon laser, and its wavelength is 632.8 nanometer, and we, as usual, we collimate a laser beam by 5 and 10 meter. We use a pinhole here, and after that we put a diaphragm, after that polarizer, and then we put printed liquid crystal cell or DDLC, dyed up liquid crystal cell. After that, we detect by a detector, which is it is connected to my laptop, and we recorded a picture by this method. Here, the polarizer's degree may be changed for our concept. Here, this picture we recorded by detector. As you see here, the diffracted beam has zeroth order diffraction, zeroth order diffraction, first order diffraction, and second order diffraction. Here we plot the intensity distribution of this diffraction order. The black plot is for a zeroth order diffraction, which is a Gaussian shape, almost Gaussian shape diffraction distribution, and the first and second diffracted order intensity distribution, like layer vortex. Layer Gaussian beam, and your vortex beam diffraction order, and After that, when we change the direction of polarization and we put at 90-degree or vertical to the surface of the dyed-up liquid crystal cell alignment, we saw the detector recorded just zeroth order diffraction, and the one, two, and first, second, third, and other diffraction order is eliminated. The distribution, the intensity distribution of this beam is plotted, and you see a Gaussian beam. After that, we want to compare this situation by each other. The first picture, which is you see, recorded by detector without any polarization in front of the liquid crystal cell, which is you see the order of diffraction. First order of diffraction is shown, and the second picture is recorded when we put a polarizer parallel to the surface, to the alignment of liquid crystal cell, and the picture is make no difference without any polarization diffraction. But the third picture is recorded when the polarization in front of the liquid crystal cell is perpendicular to the surface alignment, and here our detector didn't record any diffraction order, and here we can understand that the diffraction order of the diffraction order of the diffracted light is has polarization, and finally, we understand we have demonstrated a high performance phase correcting without polarization diffraction order using a dyed-up liquid crystal cell. The unique feature of our design is the use of planar dyed-up liquid crystal cell and the fork correcting printed on cell, which is the mechanism of on it by a dye absorption mechanism. Furthermore, it can be generated by planar cells without any external voltage nor even an external magnetic field. It characterizes the transmitted field of polarization. There are some cases in which different states of polarization need to be controlled with polarization state generators. When it is eliminated with an arbitrary state of polarization, except zeroth diffraction, the output beam has linear polarization. Finally, we use a planar dyed-up liquid crystal cell to generate the polarization fork corrections. Do you have any question?
Yes.
Thank you so much for listening to my present. Thanks.
Okay, thank you very much, Harissa.
Thanks so much.
I congratulate you and your supervisor, Professor Hoshima. So, any question, please? There is no question. I thank you again. And I would like to invite the next speaker, Dr. Pınar Özden from Muğla Department of Physics.
Thanks so much.
Okay, thank you very much. Pınar, can you hear me? Yeah.
Yes, I am here.
Okay. You can start and you can share your PowerPoint slides.
Thank you. My name is Pınar Özden from Muğla Koçman University Department of Physics and Liquid Crystal Research Groups. I will talk about Sorry. Yes. Can you see my slideshow?
Yes, everything is good.
I will talk about today wavelength depending measurements of the optical anisotropic properties of 5 CB liquid crystals. Outline of my presentation, first liquid crystals, what is nematic liquid crystal and 5 CB, optical and thermo-optical properties, finally experimental and results. As seen, liquid crystals exhibit electrical controllable electro-optic properties. They have attracted much attention in various application fields, including flat panel display and several kind of optical or electrical switched electro-optic device. Liquid crystals are very rich in terms of their optical properties. Liquid crystals have characteristic of some properties of crystals due to have orientational order and weak positional order. If the fast translation become with temperature variation, they should be thermotropic liquid crystal. If the fast translation become with temperature and concentration variation, they should be lyotropic liquid crystal. Nematic mesophase 5 CB are one of the main types of liquid crystal materials. In the nematic mesophase, the molecules have only long-range orientation order, and they tend to be parallel to some common axis, the so-called director. This mesophase is optical anaxial. Nematic liquid crystals are sufficiently sensitive to various external effects, for example, thermic, electric, and magnetic fields, deformation, and flows, exactly. The members of foreign alkyl cyanobiphenyl group liquid crystal homologs series are quite important materials for both fundamental science and display technology, owing to working capacities of some members at room temperature. 5 CB, which is a nematic liquid crystal and the member of NCB homologs, has 5 carbon atoms in its alkali chain, and its mesophase range involves at temperatures between 24 and 35 degrees. Optical properties. The birefringence of liquid crystal is a K parameter which affects the operation of liquid crystal based electro-optic device. The birefringence can be expressed as Ne minus No. The values of order parameter were obtained using different approaches. For example, Wilks method, Nog-Burst method, another modifier Wilks vector, Meyer, Zope, and direct exploration method from birefringence data. The order parameter and principal perceptual of the liquid crystal are determined from refractive indices and optical birefringence data. We use polythermic refractory technology for refractive index, were measured by using an up-based refractometer with digital thermometer from Atago and circulatory thermometer Ultratherm 200. And ocular for the refractive index measurement is 0.1%. The experimental result, the obtained experimental results shown in figure, the temperature depends of refractive index of non-aligned surface for 5 CB during the cooling progress for 3 different wavelengths. Other figure is the temperature depends of extraordinary refractive index and ordinary refractive index of aligned surface for 5 CB during the cooling progress, again for 3 different wavelengths. The variation of reflective indexes with temperature in isotropic and nematic regression is illustration in figure. As seen from the figure, the values of Ne increase as temperature decrease, while the values of NO decrease as temperature decrease towards its isotropic state. It is typical relation for polar nematics. Other figure is temperature dependence of birefringence of aligned surface for 5 CB, again during the cooling progress for 3 different wavelengths. The delta N values are seen to increase greatly as temperature was decreases because of the liquid crystal molecules tending to go to a more order state. And the temperature dependence of extraordinary refractive index and ordinary refractive index of aligned surface. Again, cooling progress for 3 different wavelengths. As seen from the figure, the values of alpha E increase for as temperature decrease, while the values of alpha O decrease as temperature decreases. And the other, the temperature dependence of polarizability anisotropy and effective geometry parameter of aligned surface for 5 CB. The delta alpha values are seen to increase gradually as temperature was decrease. Results, the temperature depends of reactive index, birefringence and order parameters for 5 CB have been investigated in the study. The ordinary refractive index increases silently, while the extraordinary refractive index decreases sharply as the temperature increases. Therefore, the optical anisotropy increase with decreasing temperature. A modified 4-parameter model has been used to explain the temperature dependence of refractive index, birefringence, and order parameters of 5 CB. The results were then compared with the obtained experimental data and found to be in good agreement with each other. Thank you for your interest.
Thank you very much, Dr. Pınar Özden from Muğla. Any question, please? I think there is no question again. I would like to thank you again. So the next speaker, Professor Nikolai Staskov from Belarus. I don't know. I can see here Yevgeny Chudakov. Do you a presenter on behalf of Professor Staskov or no? I think no. Yes, I skip the. Yes, okay. Okay, I would like to invite Yevgeny Chudakov on behalf of Professor Staskov. Okay. Please open your voice. Okay. I can see you and you can share your PowerPoint slide just now. Okay, thank you.
You can see me good?
Yeah, it's good. You can start.
Hello. Thanks for the opportunity. My name is Evgeny Chudakov. I'm a graduate student in the Mogilев State University. Topic is of the report, investigation of optical characteristic of indium sulfide thin films by spectroscopic ellipsometry and spectrophotometry methods. The relevance of studying the dependence of the optical characteristic refractive index N, excitation index K, and band gap A sub G of indium sulfide films obtained by high frequency magnetron spiriting on the annealing temperature is explained by the fact that indium sulfide is an alternative to cadmium sulfide and the development of thin films photovoltaic modules. The dependent formulas of Tauch-Lorentz equation 1 and 2 are used in literature to determine the complex permittivity and parameters N and K in inversion 3 of the film. Parameter E sub G is determined by equation 4. Using equation 5 to 8, the N and K exponents and film thickness can be determined by the spectral ellipsometry and spectrophotometry CRT methods. In this case, the dispersion is not laid down. The parameters N and K are stored by the Lagrange-Chebyshev polynomial, which describes the imaginary refractive index in equation 3. Most often, absorption coefficient alpha and equation 4 is determined for the spectra R and T in equation 6 and 7. Azimuth alpha is equal 0. It is known that the destiny rho molecular weight W and molecular refraction A of ascendant are determined by the Lorentz function. Changes in the refractive index can be explained by a change in density rho. To determine the film thickness, it's suffice to know the refractive index at the coordinates of two neighboring extrema in inversion 10. The surface and transition layers of this film substrate are modeled by the effective Bergman medium in equation 11. Next, indium sulfide films were obtained by high frequency magnetron spiriting. The angles phi and delta of all samples were measured on a UVSL2 ellipsometer at angles of incidence CLG 60, 65, and 70 degrees. Spectra T of CLG substrates at film on these substrates were measured using Aperkin-Elmer lambda 2 SUVV spectrometer, and this wavelength range from 200 to 900 nanometers with a step of 1 nanometers. And then angle of incidence theta equals 0 degrees. The T sub S, T sub P, and R sub S, R sub P spectra of the CLG substrates and film on these substrates will measure a photon RT spectrometer in the wavelength range from 250 to 826 nanometers with a step for 1 nanometers. And this slide shows schema of the study of the CLG substrate and films on substrate narrow bundles SE are divided into 2 and 4. You can see in photo above the bundles. In this case, the SE inverse problem using delta psi 2 for 3 layers for is simplified. Measured points and calculated dashed spectra of psi and cosine delta of IS-1 350 films, and then in the incidence angle of 60 degrees. Significant difference between the measured psi sub e and cosine delta sub e from the calculated psi sub TL and cosine delta sub TL is observed in the region of the interference extrema and the region of film transparency is determined by the Cauchy-Lorentz function. This difference can be clouded by spectral changes in the films, which lead to more complex dispersion dependence of optical characteristic in comparison with function 1 and 2. The solid curves psi LC and cosine delta LC are calculated by solving the SE inverse problem by the least squares method using a specially developed algorithm in which D sub F, K sub F, F sub F are restored by the Lagrange-Chebyshev polynomial for a single layer film plane parallel absorbing substrate CLG. This slide shows the measured or calculated transmissed T spectra of ES1, ES1 350, ES1 450 films, as well as calculated K spectra of CLG. ES1 is the original film. ES1 350 is the annealing temperature of 350 degrees. ES1 450 film the annealing temperature of 450 degrees. And this slide shows the dependence of the refractive indexes of film on the wavelength of the structures of different annealing temperatures. It can be seen that the annealing temperature increases, the refractive index increases. This slide shows the dependence of the extinction index of film on the wavelength, the structures at different annealing temperatures. No, this is our same thing. With an increase in the annealing temperature, the extinction index increase. This is all given by Cauchy-Lorentz function. And this slide shows the dependence of the Cauchy function on the photon energy for determining the band gap of an ES1 350 film. The first we use spectra K sub FT and formula 5. This is for and next we use spectra K sub F calculated by formula 1. This is and next spectra calculated by formula 6. And T and R spectra we calculated by formula 7, and this would like this, and then finish this spectra of T and formula 6 like this, and this and this. And next slide shows a calculated of the band gap of different methods and different temperature of annealing in indium sulfide structure. As it can be seen from the table, with increase the annealing temperature, the band gap increases. And this slide shows the dependence of the refractive index on refraction. And the molecular refraction A divided by molecular weight W ratio is a constant value. Then with increases in the refractive index, the density increases. And finally, I would like to say about the roughness of the films. It was determined by the thickness of the surface layer D sub 2. Weight taken into account that the layer consists of 50% of air and 50% of film. If you see column 1, the table shows the roughness of the film studied on atomic force microscope. Further, we calculated the values of D sub 2 and F sub 2. From this, it follows that an increase in the annealing temperature of indium surface films leads to decrease in the concentration of void F sub 2, and to a corresponding increase in the concentration of the films itself in their new surface layer. Therefore, the film's roughness R sub RMS increases. And this slide, you can see all conclusion. And that's, I think, all. Thank you for your attention. And this is literature for we use. Thank you.
Thank you very much for your nice presentation. I'm waiting for question. There is no question again. So I would like to ask some people here to give you a question.
Okay.
Dr. Golshahi, are you here? No. Okay, I have a short question. For calculating the band gap of the structure, you showed some graphics. Yeah. Here, how you calculate the band gap, by the differentiation method or by interpolating the line on the points?
Okay, I understand. 1 second. We just all this calculated about just interpolation and function. Do it as like sorry, I bad speak English. I need more translate.
Yeah.
All this do by various methods, and it's all interpolation for the function.
Okay, thank you very much again for your nice presentation, and I would like to switch the next presenter. Next presenter is Ömer Akpınar from Gazi University, and the title of talk is Titanium Doped Sapphire Crystal Growth. You can share your slide, PowerPoint slide, and
thank you.
Hello everyone, it's Ömer, PhD student, Gazi University Physics Department. Today I am going to about titanium doped sapphire crystal growth and laser application. I will give information about growth of titanium sapphire single crystal by Kyropoulos method, titanium sapphire properties, laser application, and our current studies in titanium sapphire laser production. Kyropoulos method is a way of producing large single crystals that were free of cracks and damage. In the Kyropoulos method, pure alumina and 0.25% titanium oxide raw material are placed in a crucible and brought to melting temperature. The crystallization front after the seeding process progresses gradually inside the melt. During the growth process, the crystallization front takes a convex shape towards the growth direction. At the end of this growth process, the crystal takes the cylindrical shape of the crucible. As a result, a large diameter ingot of high optical quality is obtained by Kyropoulos method. Sapphire has high transmission in the UV and IR regions. It's a material with high hardness and melting point, good thermal conductivity, tensile strength, and high resistance to abrasion. Sapphire is difficult to shape due to its high hardness, and its physical properties are anisotropic because it has a hexagonal crystal structure. The growth methods used for sapphire synthesis greatly affect the quality and shape of the sapphire produced. Titanium-doped sapphire is an ideal optical component for many optical applications, including IR detectors, fiber optic lens, missile domes, and lasers. This material is the most successful solid-state laser material in the near-infrared wavelength range due to its high saturation energy, large simulated emission cross-section, and broad observation gain bandwidth. Successfully deployed in a wide range of applications such as high-intensity physics, frequency meteorology, spectrometry, as well as pumping of tunable optical parametric oscillation. The titanium-doped sapphire laser is a tunable laser, has excellent tunability and potential to create ultra-short pulses. These lasers also possess high laser cross-section, which in turn minimizes its Q-switching instability. It emits near-infrared and red light in the range of 650 to 1100 nanometers. Pumping of titanium sapphire laser is carried out with another laser that has a wavelength of 532 nanometers, which including ND-EVO laser, frequency doubled ND-YAG laser, or argon ion laser. It combines excellent the optical, physical, and thermal properties of sapphire, and so it is widely used in scientific research. Titanium sapphire ingot with a diameter of 30 cm and a length of 35 cm was produced from the Kyropoulos crystal production device located in the infrastructure of Gazi University Photonics Application and Research Center. It was cut by core drilling to obtain a cylinder with a diameter of 55 mm. After the cut cylinder was sliced through the operative thickness, lapping, and polishing process of the double surface were started. At this stage, it is animated to reduce the surface roughness to below 270 nanometers for use in laser application. Reference. Thanks for listening.
Okay, thank you very much, everybody. Just now, I would like to ask to everybody to take a group photograph if you are agree. I would like to ask Busa and Meltem to taking a group photograph. You can open, or all of you, you can open your video cameras and yes. Yeah. I think everybody have access to open cameras. Yeah, Siamak, mine is blocked. You can give access to Dr. Golshahi to open his camera. I think we should get access. Yes, we can see. Mohammad Reza, please open your mask. Thank you very much. So,
Smile, please.
go on, Süleyman Hoca. Mehmet Kaya on the way, I think, just now. Gürkan Yeliz, thank you. So thank you everybody for taking photograph, and just now I would like to close this session, and I think the next session will start at I think 10 minutes later. Okay, thank you very much.
So, how was Turkey?
So Turkey was... Wow. Yes. So Turkey was, wow, yes.
Turkey. So Turkey was... Wow. Yes.
So how was Turkey? So how was Turkey?
So Turkey was... Wow. Yes.
No.
Hello, everyone. This is Güven Turgut from Erzurum Technical University. Everyone, welcome to fourth session of today's program. We will continue together. Our session will take about 2 hours. First, we will start with invited speaker, Dr. Shiamak Golshahi from Islamic Azad University, Department of Physics. Is Dr. Shiamak here?
Yes, yes, yes, yes. I wonder if you hear my voice.
Okay, I hear your voice. You can start if you want.
Okay, yeah. Just let me. Okay. Thank you, Professor Turgut, for inviting me for the talk. May I start it?
Yes, you can
Yeah.
start.
Yeah, thank you. When I was invited to just have a talk in this conference, I just searched the topics that I worked on it during the last years and found something more interesting, which was related to the graphene material. As you know, is the 2D material with lots of application, the mechanical one, the electrical one, the photo electric applications. And this is one of our last research that I just carried out by the help of my colleagues, Dr. Hayatian and Professor Ana Maria from Portugal. And let's jump into the topic. In this work, we have synthesized nanocomposites of graphene oxide and zinc oxide. The process is things that I'm explaining here. We use graphite powder as we ICL ones. These are the high quality graphites. You can use other precursors with lower qualities, so it will affect your results. But I mean, you can do it with cheap materials also. But we did it with high quality graphite ones, and we used acidic environments and also an oxidation agent, which is a strong one. By the help of these two, you can intercalate the oxidation agent into the structure of your graphites, and as a consequence, you can loosen the bond between these sheets. As you know, these sheets actually are graphene sheets, which make a graphite structure, and by the help of the oxidation agent that we have used, permanganate potassium, you can loosen these bonds, and consequently you can reach structures of graphene with low thicknesses. But when I say low thicknesses, I mean thicknesses in the range of 2 to 10 layers of graphene. And but the drawbacks of this method, the method that we have used, is this: as a consequence of oxidation effect, you have lots of functional oxygen-related groups on your sheet, and if you're going to just get application related to the electrical properties of this material, you need to reduce this material. I mean, you need to break these bonds. And that was the things that we were searching for. So we used zinc oxide and made them composite together by the help of hydrothermal technique. As you know, in the hydrothermal technique, you use low to moderate temperature. We have used 120 degrees Celsius inside the autoclave, and by the help of enhancing the pressure of the ambient, you ease a chemical reaction, which, as you know, it can easily makes you nanocomposites of metal oxide family and also the graphene one. And the quality of the products which has used these methods is normally high. We just dispersed graphene oxides that we first synthesized it by the sonication, and just mixed it with a solution of zinc nitrate and a material which is hexamethyl tetranamine. I will mention about this material more and why we have used this material in the process of preparation, and we also just enhanced the pH of the precursor solution to 11. In the method of hydrothermal technique, it's required to enhance the pH to this range to actually enhance the rate of the reaction, because you need hydroxyl groups. And if you enhance the number of hydroxyl groups, the rate of the reaction will enhance this. This is the final precursor solution that we have used. And when we just enter the solution, when we pour the solution into the autoclave, you can control the synthesis parameter. The parameter that we selected was the time of growth. We just varied that between 3 to 18 hours. So the interval is long. We started from small time to low time to high time of growth, and we gave the precursor solution the chance to change it. We characterized the sample in the way that you are just seeing here. We start with surface morphological properties, and we use scanning electron microscope. You can see the result here. The result just is related to the sample, which is synthesized within 3 hours. We just observed two abundant morphologies here. The one that you can detect easily are rods. These are rods have the cross section of hexagons, which is the preferred structure of zinc oxide. As you know, the structure will form as hexagons, and that was exactly the things that we observed. The other morphology that we detected, which you can see here, was actually spindle-like grains. I call it spindles. And you can see some sort of branching, the initiation of a branching on this spindle after 3 hours is just taking place. And another thing that we mentioned was the presence of graphene that was evident in the surface of the samples. You can see that here, I have used a margin here, the red one. You can see you can see that the rods, the big rods, is conserved by something like a glue, but actually it's not glue. It's that's the graphene one. We have enhanced the time to 6 hours, and we saw exactly the same morphologies, but the only change that we detected was that the spindles, which showed an initiation of the branching, just continued its branching process, and it converted into joint spindles, which looks like flowers that we call it nanoscale flowers. So for 6 hours, we had two morphologies. One was these ones, flower ones, or spindle, fully grown spindles, and also the ruddy ones. You can see here, you have here the flowers and also these big rods. And the interesting thing was that you can clearly see the structure of hexagons here, which is the preferred crystal structure of zinc oxide. And here, if the length of this hexagon enhances, it means that you are adding a zinc atom to the cross section of this structure in the C-axis that we call it 002 crystal plane, and this is the preferred growth direction of zinc oxide. Here you can see at 6 hours, like 3 hours, the presence of graphene sheets. You can see graphene sheets here, and you can easily see that it's somehow transparent, and the light is passing. Actually, the light, no, the electrons is passing through the graphene, so it's giving you a graph, as you can see. And these rods are actually constrained to the structure of grain, and they are showing the bond which is formed between these two materials, different material, the zinc oxide one and the graphene one. When we enhance the temperature to 9 hours, actually no difference can be detected. But when we enhance it to 12 hours, the difference was clear. I just made a difference between 3 hours to 12 hours, but actually for 6 and 9 in comparison to 12, that was the same. You can see here the length of these tubes are small in comparison to 12 hours, which the process of enlargement just continued. It means that the building block, which is forming this material, this structure, is still there, and the process of forming and accumulating and actually crystallization is still continuing, as you can see at 12 hours. Here also you can see the presence of just concentrate zinc oxide rods inside the graphene structure, and as you can see, the thickness of graphene is too low, as you can see the other side of that. And the interesting thing, which initiated at 12 hours, was a phenomenon interesting phenomenon, which, as you can see, some of these rods is passing through the thin layer of graphene, or graphenes, actually, we should say, because the thickness is not just one layer, maybe more than one. You can see some ruptures here. 12 hours was the starting point of rupturing of graphene sheets, and you are making into pieces by the use of these rods. We continued the process at 15 hours. We just detected that the rods is still there, the length is enhanced. We still can see these hollow tubular long hexagons, as you can see, and we can see also some structure, the roddy ones, which does not have the defined form of others, it looks like they are disturbing, they are deforming, and they are exploding, and it seems that they are not growing anymore. I do not have a micrograph at 18 hours, but it shows that after 15 hours, the process of enlargement just comes to an end, and this sort of deformation is enhancing. Another thing is that the rupturing, which started at 12 hours, has continued to 15 and has reached a saturation at 18 hours. As you can see in 15 hours, you can see here some evidence of ruptured. You can see here better. These are the sheets of graphene. They are totally torn apart. Here you can see as a consequence of the growth of zinc oxide. To make a quantitative study, we just used software, the image processing software, to just calculate the size of the rods. As you can see, I compared the rod length and rod width as a function of growth time here. You have a jump, you have an increase from 3 hours to 15 hours, and a decline in 18 hours. And these bars are standard deviation here, actually. You can understand that these just shows and statistics of the size, distribution size of length of the rod and the width of the rod in different growth time. And the wider, it means that you have different sizes at 18 hours, which the mean size is something like that. So that was the experimental data, experimental observation of the surface. But what's happening behind this growth mechanism? We just proposed a growth mechanism to explain what happened. As I explained, I use zinc nitrate as the source of zinc. So it will release the ion of zinc, and if we follow this successive chemical reaction and just take a look at it in general, we can understand that we have two methods for producing zinc oxide. The first one is here by the help of the ion zinc, and also hydroxy agent, you can reach zinc oxide. And another one is this agent, ZnOH4 2-. This agent actually is one of the main building block. I call it building block of zinc oxide. If the concentration of these components enhances in the ambient, you should wait for an enhancement in the rate of zinc oxide formation and nucleation, and also after that the growth of zinc oxide. So we have two way of production. I just would like to concentrate on this one, on this building block. As I told you, more than zinc nitrate, we have HMTA. That in this explanation, I'm putting HMTA aside from the mechanism that I'm proposing, and I tell you the reason in next slide. Okay, just take a look at this reaction. You need to consume 2 OH- here. 2. It means that to couple. It means that you need to consume 4 OH- here, and 2 will come back to the reaction. So if you continue this successive reaction, you should wait for a reduction or a decline in the number of OH-. So what will happen if the number of OH- reduce? It means that you cannot have enough building block here, because for making this building block, as I told you, you need lots of OH minus. And if you reduce the concentration of hydroxy as a result of the continuation of the process of the growth, it means that this component, the concentration in this component will decline drastically. And if it just declines, as a consequence, ZnOH2 concentration will go high. And as you know, this is a material which precipitate inside the structure, and when it precipitates, it does not enter the process of zinc oxide growth. So your product should contain zinc oxide and ZnOH2 if we enhance the time of growth. And that was exactly the things that we saw in the X-ray pattern, X-ray diffraction pattern of our structure. As you can see here, from the black one, the red one, the blue one, just go up. The time of growth is enhancing from 3.6 to 9 to 12 to 15 to 18. And as it reaches 15 and especially 18, you can see new phases. Actually, these are ZnOH2, which are present in the structure of zinc oxide as defects. And the process that I explained was the main cause for the presence of these agents. Okay. Okay, let me add HMTA to the proposed mechanism, because we added that one. HMTA is this structure that you can see, and the following reaction will be there when you add HMTA in the precursor solution. As you can see, you release lots of OH minus. So to the point that you have HMTA, to the point that the time that the concentration of HMTA is still high and is still present in the precursor solution, you are releasing OH minus inside the ambient, and the process of growth is still continuing. That was the thing that we detected, that we continue the growth time, and the size and the width is still continuing, becoming bigger and bigger and bigger to the point of 15 hours. And to that point, the process that we explained, now at 15 hours, the concentration of HMTA is reached the point that we can say that it's not there and it's not effective anymore. So the process that I explained in this slide become the prominent phenomenon, and what will happen? So the process of growth stops, and ZnOH2 just rebuilds. Okay, if you add up the things that I explained here and here, the role of HMTA, you can understand what's happening inside the autoclave. Actually, HMTA, based on the literature, HMTA plays triple role. The first one, as I told you, is to release hydroxide inside the structure that we guess that it continued to 15 hours, because after 15 hours of the continuation of the growth, this agent has come to an end. So you do not have any HMTA anymore, and so the growth stopped. Another thing which is interesting and justify the reason of this hollow structure is the presence of these agents. As you can see, this positive charge can be absorbed to any polar phases with negative charge, and you have it inside the zinc oxide. If you just take a look at the conventional cell of zinc oxide, you have this plane here, hexagon here, which is polar one, and the side planes, which these side planes are non-polar ones. In the top you have zinc oxide, zinc, and in the bottom you have oxygen, and they will be accumulated successively along the z-axis. And as a consequence of this accumulation, you can see that these, this plane is the polar one, and these are the non-polar one. So this agent, we guess that it's absorbed to the polar faces and stopped or slowed down the process of growth along this plane. That was the reason for the hollow structure.
Dr. Shamak,
yes.
Could you a bit fast? You have 5 minutes.
Yeah. Okay. Thank you for reminding me the time. Okay, let me jump into the XPS spectra, because the third role which we just play for HMTA is that it can play a role of clinching. It make a joint structure between carbon and zinc. To just show it, we required surface compositional properties, and we did it by the use of XPS. We have here the XPS data of carbon 1s orbital. We just carried out the experiment for 6 hours and 15 hours, and we deconvoluted the data. You can see the red one and the blue one here, and these are the results of deconvolution here. The main peaks are these two peaks. The red one, which is carbon-carbon bond. As you can see, these are a strong bond between the carbons, which forming graphene structure, and also we have another one which was the carbon OH, or epoxy carbons, which we expect based on the material that we have used in the precursor solution. We have used materials which release high concentration of OH, and its release means that they come to the structure, and the chance of being attached to the graphene will go high. And you can see that the OH bond with carbon in 15 hours is enhanced in comparison to 6 hours. This is important. If we just take a look at this one also, we have calculated the oxidized carbon, the ratio of oxidized carbon to unoxidized one. As you can see that this is growing. So the functional group for 15 hours, or generally the samples which were grown at high growth time, is higher than samples which were grown at lower times. It means that in comparison, the samples which were grown at lower times are more reduced in comparison to the samples which were grown at higher time, which are more oxidized. So we can call these samples as graphene oxides, and these ones as partially reduced graphene ones. For the application of the samples for the powders which we synthesized, we just checked their photocatalytic and also the catalytic properties. This is the setup that we have used. We have used visible light. Normally, researchers just use UV light. As you know, the bandgap of zinc oxide is wide, and is something around 3 or more than 3 electron volts. But our samples bandgap was less than 3 electron volts. So we used a visible light to excite them to degrade the dyes, industrial dyes, and we checked the process of degradation of methylene blue. As you can see, we have used a mixture of a solution of methylene blue, and we added nanocomposites or nanocomposite to the structure to see what will happen. We left the samples 1 hour in the dark field, and after that we started illuminating, and we just in the interval of 30 minutes we illuminated the samples. After each illuminated, and after each period of illumination, we just extracted, take it out, a small part of methylene blue. We just removed the photocatalyst from dye by this centrifuge, and we just checked the UV absorption spectra. As you can see, these 3 samples are completely different to these ones. Just check this short pick. The black one is the start point, and the red one is the peak after 1 hour being in the darkness. It means that without excitement with light, your samples is just degrading the structure. But when the time of growth enhanced, this effect just you can see is not prominent like these 3, as you can see. And when we just illuminated the samples, it totally degraded this the dye, which is a good result. But in comparison, the samples which were grown at higher times does not show such an effect. I just showed the same result based on the concentration of dye as the ratio of the concentration of dye at different times after irradiation, before irradiation, and to the concentration at the starting point. You can see we started from here, and it just declined in the dark ambient. I just divided the samples into 3. These 3 are the samples which were grown at time less than 9 hours. And these belong to the group that I call it group 2, samples which were grown with higher synthesis time. And it's clear that this group is showing better results. Why? As I told you, here in this group, you have 2 morphologies. You have rods, which are smaller, and you have smaller structures, which we called it spindles or flower structure. As you know, if you reduce the size of your grains in the surface, so the reactivity of your product will enhance this. And if the reactivity will enhance, you should wait for a better catalytic and also the photocatalytic result. You can see after illuminating also the concentration of dye just reached something nearly 0. So it means that it's totally exploded. And but the result is totally different to the group 2, because in group 2, as I told you in XPS results, these red ones, which were grown at higher times, are mostly graphene oxide. So here you have oxidized agent, you have oxygen agent, you have epoxy agents. You have this functional group on the surface of graphene, so this cannot attack dye and interact with that one. So the results is not as good as these group 1 members.
Dr.
These are
Shema,
the,
I'm sorry, I am.
Yeah, I'm at the end of the presentation.
Okay, we don't have any more time.
Okay, it's just the conclusion, and thank you for letting me just presenting my work. Here is a village in the north of Iran. You are all invited to that. The name is Masule. You can Google it if you want.
Okay. Thank you very much for your useful talk.
Welcome.
And
welcome. I'm waiting for questions.
Yeah, we can take the questions, and if you have a questions, you can text. I think there's no question now.
Nothing.
I think yes, we don't have any question now. Actually, I have a question for you.
Yeah.
How can you confirm the thickness of the graphene?
Actually, the main experimental method that researchers use is atomic force microscope. You know, it's a little tough for samples which were formed in the powder. But if the result is something like flakes, you can easily do it by the help of atomic force microscope.
Okay.
I did it.
Okay, thank you. Thank you very much.
Yeah, welcome.
Now, now our speaker is Zekeriya Mehmet Yüksel, is from Pamukkale University, Department of Physics. The title of
Well, I can't hear you. Your microphone is closed.
Sorry, now can you hear me now?
Yeah, it's good
Okay.
now.
I think there's a technical problem. There was, and okay, you can start
Okay,
your talk.
I have shared my screen.
You
Is it okay?
have 15 minutes, you know.
Yeah, okay. Hello everyone, I'm starting. Today I will talk about the evaluation of optical properties of hexagonal and circular solid core photonic crystal fibers for various structural design parameters. Our outline is we start with our purpose, then what is a photonic crystal fibers, then our baseline index guided solid core photonic fiber, which commercially produced, and our methods, our structural parameters, and the physical and optical properties, then comparison for with experimental and theoretical structures, and the conclusions. Okay, the main aim of this study is examining the effect of structure parameters on optical properties. It is lead way in obtaining the more efficient structures by examining the differences between the optical properties of the circular air hole, which we called PCF1, and the hexagonal air hole structures, which we called PCF2. Okay, and what is a photonic crystal fiber? Photonic crystal fiber, PCF, have periodic optical structures in the wavelength scale, which enable unprotected control over the propagation of the light, and the light propagation in PCF with a lower reflective index due to their air holes, and in the cladding region is more spurial than the conventional fibers. Applications for photonic crystal fibers are spectroscopy, metrology, biomedicine, imaging, telecommunication, industrial machining, and the military technology, and etc. On the figure 1A, we see a standard optical fiber, and the figure 1B, we see index guiding photonic crystal fiber, and the image C, we see a hollow core photonic band gap fiber. So we based a commercially produced photonic crystal fiber, which called NL2.3-790-02. This fiber was produced by Nekata NKT Photonics, and we characterized this the photonic crystal fiber with computational methods. Here in the figure 2, we see the index guided solid core PCF. And the figure 3, we see this fiber SAM image. And some of the physical properties of this fiber is the core diameter 2.3, and the the pitch value is 1.6, and the other physical properties are here. Its optical properties, which is important when the zero dispersion wavelength is 790 nanometers. Dispersion slope at zero dispersion wavelength is 0.64 PC nanometer kilometer, and the attenuation value is at zero dispersion wavelength 25 decibel per kilometers. Okay, we started this
photonic crystal fiber, and they used two different methods to calculate its properties. First of all, we used the finite difference agent mode method by using the numerical mode solution software. The FDA method calculates the fundamental models of fundamental modes by solving the electromagnetic Maxwell equations as a function of frequency on the fiber cross-section network. And the other method is the perfectly matched layer. Perfectly matched layer is surrounding the coating region, which are used as an absorber boundary condition to prevent the mode reflection from the boundaries of the simulation domain to the core region. In here, figure 4, we see our numerical image for the outer scala cladding of designed PCF. We have two different models. Model 1, which we call PCF1, the air holes are circular, and the model 2, which we call PCF2, the air holes are hexagonal structure. And the other pictures, we see their structure parameters. If we see the structure parameters more clearly, the DC is the core diameter, both structures, and the D is the air hole diameter for the circular air hole, and the S is the diagonal of hexagonal. And we have the pitch value. Pitch value is the distance between the air holes. And we define another parameter, which we called F, relative air hole diameter. For PCF1, our F parameter is D divided by pitch, and for PCF2, our F value is S divided by pitch. So we can compare these two structure with F parameter and pitch parameters. Okay, so we started with the pitch parameter 1.5 micrometer, and our F values is as you see 0.8, 0.85, 0.90, and the 0.95. So the DC parameters and the D parameters, we try to do the same pitch values and the F values for PCF1 and the PCF2. Okay, our pitch values and the F values are same, but our core diameters are different because of the shape of the structures. So after we designed these parameters, designed the structures, we started their optical properties. We start with the dispersion. Dispersion can be defined as a change in pulse with per unit propagation length, which splits in the wave into the different spectral components. In this formula, D is our total dispersion, and the real part of effective. C is the speed of light and the wavelength. Our other optical properties is nonlinear coefficient. Nonlinear coefficient is a measure of the ability to confine the high intensity of light. In this formula, N2 is nonlinear refractive index of silica, which we used in this fiber, and the area effect and the effective nonlinear area. Okay, what is effective nonlinear area? Is indicates the effective nonlinear area quantifies the total area enclosed by the confined mode in the transverse direction. In here, the A parameter is the electric field intensity propagation in the transverse direction. And other optical properties is confinement loss. Confinement loss measures the value of the light field energy leaking from the core area as the light wave splits in the fiber core. And in here, we use the imaginary part of the effective indicates. All of these structures results are here: effective nonlinear area, nonlinear coefficient, and the zero dispersion wavelength. We simulated 32 different structure, which 16 one on the PCF1 and the PCF2. As we see, at the same pitch and the same F values, zero dispersion wavelength is higher than is getting higher if we get the circular one to the hexagonal one. Hexagonal structures zero dispersion wavelength is higher than the circular ones. Okay, and the area effective effective nonlinear area values are same like the zero dispersion wavelength. Hexagonal structures area effective. Effective nonlinear areas are higher, but the nonlinear coefficient is getting lower from circular one to the hexagonal one. These are the differences between these structure parameters than the optical properties. Okay, if we see the dispersion profile with the PCF1 and PCF2, as we see here, at the pitch value is 1.5. The dispersion value is higher than the hexagonal one, and the curve is, as you see, turns back. But if we go to the the other structure parameter, which is pitch is 2 micrometer, the dispersion curve is going to the linearism. So in here we have some interesting properties of the pitch value is 1.5. If we see the pitch value is 2 micrometer and the pitch value is 2.3 and the pitch value is 2.5, there's no turning as like a curve in this dispersion values. As we see, we higher the pitch value, the dispersion values are getting higher, and all structures have different zero dispersion wavelengths on the simulations. Okay, if we compare our experimental and the theoretical values, the experimental values are core diameter is 2.3 and the theoretical one is 2.4. We took the pitch value is 2 micrometer and the zero dispersion values are also same. And our dispersion slope is also same. And we have the same attenuation values. Also, nonlinear coefficient and the effective nonlinear areas are so close to each other. So we can simulate the conventional fiber, which we PCF2, the F value is 0.95 and the pitch value is 2 micrometers. If we continue our results, the dispersion profile with F and pitch values, F is, as we see, the F values are getting increased. Our dispersion is getting decreased. As a pitch value getting increased, our dispersion is decreased too. These are our results with the F and the pitch values for dispersion profile. And the effective mode area and the nonlinear coefficient relation for the F values is getting higher, but our pitch values is fixed at 2.0 micrometer. As the F value is getting higher, our effective mode area is decreased and the nonlinear coefficient is getting higher for each F value. And otherwise, if you see our pitch value 1.52 and the 2.5 as a fixed F, we fixed the F value at 0.95. We see the same as the F values. As a pitch value is getting higher, our effective mode area is getting higher, and our nonlinear coefficient is getting lower. For conclusions, in this study, different air hole structures were investigated. The hexagonal structure with 2 micrometer pitch value and the 0.95 F parameter was computated with the conventional structure. Both structures has the same zero dispersion and the attenuation values. For the pitch values, the pitch values increase for all structures. The zero dispersion wavelengths and the nonlinear coefficient values is increased, and for the pitch value increase for all structures, our effective nonlinear area is decreased. For the F value increase for all PCF structures, the zero dispersion wavelength and nonlinear coefficient values are increased, and for the F value increase for all PCF structures, our effective nonlinear area is decrease. And for the PCF2, which one is hexagonal air hole structures have a higher effective nonlinear area than the PCF1 with same pitch and F values. And the PCF1 structures have a higher nonlinear coefficient values than the PCF2 structures with the same F and pitch values. The dispersion curves of the PCF2, which is, I say again, hexagonal air hole structures have a more horizontal graph curve for the lower slope at zero dispersion value than the dispersion curves of PCF1 structures. Well, this was our work, and thank you for your attention. Any questions?
Thank you very much. We can take the questions. I think there's no questions now. Okay, we can pass the other speaker now. Thank you very much.
Thank you
for your presentation. And now our speaker is Göktuğ Gencehan Artan from Arpkule Business Center. And I think Göktuğ is here. Göktuğ is here now. And you can start.
But I couldn't share the screen. Can you see the presentation?
No, I couldn't. Yes.
You can see it, right?
Oh, no. Okay, you have 15 minutes now.
Okay.
Thank you.
So thank you for the introduction. My name is Göktuğ Gencehan Artan, and I'm working in TEOPS, which is an electro-optical systems company, which I will give you a review on. And my presentation is more of a review type of presentation than an experimental one. And I will try to explain the future trends of electro-optical and infrared systems for airborne ISR platforms. I will first make an introduction about the company, just a one-slide introduction, and then the introduction about what I'm going to talk about. And then I will talk about the precise positioning and stabilizing platforms and the sensors that are used on these platforms. And then I'm going to give some system examples for ISR systems. And finally, I will talk about the future trends of these systems. So TEOPS is an electro-optical company based in Turkey. And our main area of work is electro-optical systems design and mechatronic system design. So here you can see a gimbal. We have experience on both electro-optical side of it and mechatronics side. We have capability for system integration, and also when these systems are integrated, we have capability to test them and verify them. We also have detector and cooler maintenance, repair and calibration laboratory, and also lens maintenance and repair laboratory. So as an introduction to the topic, ISR is the first letters of intelligence, surveillance, and reconnaissance. And ISR is the process of gathering information from a variety of sensors to make intelligent decisions. And these ISR systems are mostly what you hear as electro-optical pods or electro-optical targeting systems. And they have been used in aircraft for many years, but now it's mostly being used on UAVs, unmanned air vehicles. And as you know, the unmanned air vehicle market is growing a lot in recent years, and the market is expected to be around $135 billion in the next 10 years. So in order to compete in this market, these UAVs and also the subsystems have to be very cost effective. So the electro-optical and infrared systems for the ISR platforms have to have very high precision. And by precision, we mean that the system should have a very good stabilization, and also the sensors have to be high resolution. And there are many sensors used in such systems. And first of all, you need a visible daylight channel or a visible near IR channel or a shortwave channel for imagery that is close to what we are familiar with. And then you need a thermal channel, which is mid-wave or long wave. And also there are some laser systems involved, which is the most common laser system used on these systems is laser rangefinders. These systems have to be rugged, and it should be able to withstand very harsh environmental conditions. But since it's going to be used on UAVs, it should also be lightweight. And as I said in the previous slide, these systems have to be very cost effective. So here you can see a video from the F-35 airplane's electro-optical targeting system. This is an infrared image, and you can see the stabilization is very good. On the left side, it's locked onto a truck which is in a road, and on the right side, you can see that it's locked onto a single point while the airplane is turning. So you can clearly see that the stabilization is very good, and also the resolution is very good. But I have to say that this was a system that was designed more than 15 years ago. So right now the technology is much better, and the systems have to be much better than this. Just a brief overview of the different generations of gimbals. The first generation was used a long time ago, and it's just using inertia for mechanical rate gyroscope. It's only using inertia, so it's not using any actuation for stabilization. And for the second generation, this is the ICLLT 300T. For the second generation, uses rate stabilization for each axis, and it has 2-axis motions. It's cost-effective and lightweight compared to generation 1, but the stability is much worse. It's not as good as mechanical rate gyroscopes. And the actuation is done by direct drive or gear. In generation 3, you use 4 axes instead of 2 axes. The outer 2 axes are for positioning, and the inner axes are for stabilization. And there's also passive isolation for vibration. And these tend to get much smaller and much more lightweight. For the fourth generation, there's active isolation for vibration, and the actuation is symmetric, which means there are actuators on both sides of the axis. And finally, the fifth generation, which there isn't a product yet from any of the big companies. It's a gimbal-free design, but it has 6 degrees of freedom. And these use very new technologies like voice coils for actuation and flex pivot elements for mounting. So when we come to the sensors, there are different options. If we talk about the visible and visible near IR sensors, the advantage is visible images are very familiar, so users want to have visible images on their systems. And it's very high resolution, so you can get crisp images. However, the disadvantage is daylight requires light. So you need a light source, or in low light applications, you have to use, if you don't want to use thermal imaging, you can use very near IR, visible and near IR or near IR. Shortwave has a very good advantage in fog conditions, and it's also better in low light applications. As you can see in the picture below, on the right side, it's a shortwave image. On the left side, it's a visible. So if there's a fog that you can't see with your eye, when you look with a shortwave camera, you can see more clearly. And when we come to the thermal side, if we compare midwave and long wave, midwave has the best image quality because of the smaller wavelength, and the technology in the mid-wave detectors allows it to be smaller now with the hot detectors, which is high operating temperature detectors, which I will get to later. And for the long wave, instead of cool detectors, you can use uncooled detectors, which are also getting much smaller, and they are very low power. So if we talk about some system examples, I'm sure you've heard of this system in the news maybe. This is L3 Harris Westcam MX15. It's a very good product in terms of size, weight, power, and performance. And it has 4-axis stabilization, HD sensors, and laser systems on it. Another system example is Aselsan's MGO CATS. The good side of this system is it has a common aperture. So it takes different wavelengths from a single aperture, and it also has some laser systems. Octopus ISR Epsilon 180 is a system that was especially designed for UAVs, and it's very lightweight, and it has very high resolution sensors. So if we talk about the future trends of the detectors, the cool detectors, some of you might know that the detector pixel pitch sizes are getting smaller each year. So for the past 20 years, where we used to have 30 micron pitch, now we have less than 10 micron pitch, especially for the mid-wave region. And you can see 2 detector examples here. On the left is the Daphnis detector, which has HD resolution and 10 micron pitch. And on the right is the FLIR Neutrino, which has a 8 micron pitch and is also HD. And I have to say that because of high operating temperature detectors, now the coolers that you see are getting smaller, so the overall system can get smaller as well. And there's also uncooled detectors. Uncooled detectors used to have very low image quality, let's say 10 years ago, but right now, as you can see in the image, there's a very high resolution image, and the sensitivity is very low as well. There's less than the sensitivity is less than 60 millikelvins, and the pixel pitch is also going down. Right now, you can find products with 12 micron pitch, and the resolution is HD. And what's the best advantage of uncooled detectors is, of course, the cost. And as the cost gets lower, it makes industrial applications possible. So even some cars have thermal imagers because of this uncooled technology. In the optics side, optical designers want 2 things. They either want large apertures or long optical paths. To have large aperture, you can use a common aperture for different wavelengths. And there was another presentation on this from a colleague in Tai. And for long optical path, you can only fold the optics. So on the right, you can see an example of Ophir's zoom lens, which has a folded optical design. So basically, it folds the optical path using 2 mirrors to make a smaller optic with higher focal length. And also, it's much smaller compared to the old generation. So as a conclusion, the technology is increasing very fast, and it's enabling us to make systems which are smaller with higher performance. Thank you very much. If you have any questions, I can answer.
Thank you very much, Göktuğ. We can take the questions now. I think there's no question.
Thank you very much.
Thank you again. And we can pass the other speaker now. Dr. Ali Emre Gümrükçü from Gazi University Photonic Application and Research Center now. Is Ali Emre Gümrükçü here?
Yeah, I'm here.
Okay, you can start.
Thank you.
You're welcome.
My name is Ali Emre Gümrükçü. I am a researcher at Gazi University Photonic Application and Research Center. Today, I'm going to talk about our latest research about the effect of sputtering conditions on silver thin films. Our aim of this research is make a low-E glass. We are consuming energy for cooling and heating. And as you can see on the diagram, we are losing nearly half of this energy by windows. To stop energy waste and use our energy more efficiently, we can use low-E glass. Low-E glass has a simple purpose. It doesn't let heat transfer between inside and outside. And as you know, heat is radiating in near infrared region. And we are expecting from low-E glass is highly transmittance in visible region and low transmittance in near infrared region. This is the basic low-E glass structure. It's called sandwich structure. The commercial products have more layer than this, but the working principle is same. There is a metal layer between two dielectrics layers, and these metal layers blocking infrared radiation, and the electric layers are protecting these metal layers and also giving high transmittance in visible region. This is our structure. Differently with the basic structure, we add aluminum oxide as a buffer layer because most of the glass production process includes heat process, and during this heat process, some elements which is inside the glass can be diffused through the low-E structure, and this buffer layer can preventing this diffusion and also eliminate the effect of substrate. We choose silver as a metal layer. It's a very common and popular in these applications because it has a natural blue color and low resistivity. And we choose as a dielectric layer aluminum zinc oxide. It has a high compatibility with silver, low cost, and also giving high transmittance in visible region. This is our system, our magnetron sputtering system. We did all this coating with this system. We try to determine coating conditions of silver thin films. Firstly, we change the coating pressure. And secondly, we tried different DC power. And finally, we coated silver thin films with different thickness. These are optical graphs of silver thin films with different pressure and power. All silver thin films thickness are 10 nanometers. The left graph shows the different pressure samples. When we look at the graph, we can say that when we increase the coating pressure, the transmittance is decreasing in all measured regions. Because increasing coating pressure, enhancing density of the thin films. Basically, we want two things from low-E glass. High visible transmittance and low near infrared transmittance. And 5 SCCM samples giving highest transmittance in visible region, and 50 SCCM sample giving lowest transmittance in visible in near infrared region. Because of that, we choose both of them, and we continue with these parameters. Thereafter, we try to find the suitable DC power, and we changed the power 25 watt to 100 watt. And as you can see on the graph, there is no significant difference, but for both pressure, we obtained best result with 25 watt DC power. And after that, we changed thicknesses. The left graph belongs to 5 SCCM samples and right graph belongs to 50 SCCM samples. When we look at 5 SCCM samples, 5 nanometers silver thin films doesn't show film continuity because we can see an absorbance in visible region. But when the thickness reaches the 7 nanometers, it has a continuity. And when we look at 50 SCCM samples, all thicknesses have continuity. And we try to understand these differences, and we did some other analysis. This is our electrical results of samples. Sheet resistivity is quite important for emissivity calculation. Lower sheet resistance means low transmittance in near infrared region, and this result matched up with our transmittance results. And we can say the 50 SCCM 5 nanometers samples are better than 5 SCCM 7 nanometer samples. But there is an interesting result here. Normally, when you increase the coating pressure, the sheet resistance will be increased because of the grain number of grain boundaries. But in our research, we show the opposite of this situation. Try to understand this situation. We'll look to the literature, and we saw that if your thickness is less than 30 nanometers, the continuity is much more effective than grain boundaries. And it means we have some continuity and connection problems with some of samples. To understand this continuity problem, we performed SEM analysis for see the surface of the sample. When we look at the images, we can see there are a lot of gaps on the surfaces, especially 5 SCCM 5 nanometer sample has too much gaps, and because of this, it has a continuity problem. You can see some other gaps in red circle. And when we increase the thickness and the coating pressure, this number of gaps is decreasing. As we know, metal atoms prefer Volmer-Weber growth mode because of their energy is much more than metal oxides and other substrate atoms. So they are building, they prefer islands-like structure. When you increase the thicknesses, it's turned to Stransky-Krastonov growth mode and can obtain continuity. This is they explain the meaning of gaps on our film surfaces. To make elemental analysis and prove these gaps, we did XPS analysis. As we see, all samples have silver atoms on surfaces, but especially at lower thicknesses, we can observe zinc atoms. And this means there is some gaps on the surface because aluminum zinc oxide layer is under the silver layer. And when we increase the thickness and the pressure, the intensity and ratio of zinc atoms decreasing and become lost at 10 nanometers. This is our SIMS analysis. We did this analysis for understand thickness of layers and their situation. As we can see, we obtain thickness what we want, and also another important result, system can be detect zinc atoms for 5 SCCM samples much easier than 50 SCCM samples, and it shows that there is some gaps on the silver thin film surfaces. We saw that 5 SCCM 5 nanometers sample has continuity problem, but 50 SCCM 5 nanometer sample has not. And also 50 SCCM sample shows a better result than 5 SCCM samples. As I mentioned before, it's related with silver atoms energy. In sputtering systems, when we increase the coating pressure, the atoms which are scattering from the target are exposing much more collision with argon atoms. And because of this collisions, they are losing some of their energy. And as a result, the silver atoms can prepare layer by layer growth mode. To understand this behavior, we performed, we analyzed the surface energy of the silver thin films. We used contact angle method. We used the ionized water for droplets, and we measured the angle. And as you can see on the graph, when we increase the thicknesses and coating pressure, our contact angle is increasing. It means that sample surface getting more hydrophobic. And also we looked the literature to understand this meaning, what is this mean? And we saw that when the contact angle degree increased, it means surface energy is decreasing. So when we increased pressure, we decrease the energy of silver atoms, and because of that, they prefer layer by layer growth mode, and we can obtain 5 nanometer silver thin films with this. And finally, this is the emissivity value calculation of our structure. There was a formula is giving emissivity value with using sheet resistance data. When we calculate for 50 SCCM 5 nanometer sample, the emissivity value is 0.08. And when we compare this result with industrial products, most of them emissivity value between 0.05 and 0.20, which is show that our structure is suitable for low-E glass. As a conclusion, we try to find suitable conditions for our research. We did some analysis to understand behavior of silver thin films, and as a result, we can solve that. We can change the surface energy of silver thin films with changing coating pressure, and which shows a better performance when we compare much more thicker silver thin films. And thank you.
Thank you very much, Dr. Emre. We can take the questions. I think there's no questions for your talk. Now we can pass the other speaker, Büşra Güloğlu Bülbül from Gazi University Photonic Application and Research Center. I think Büşra is here. Yes, Büşra, you can start your talk.
Yes. Can you hear me?
Yes. You can go now.
Hi, I'm Büşra Güldoğdu, doing my master degree in photonics application sciences and engineering at Gazi University. Today, I will give you information about the optical filter we are trying to develop. I am involved in the development of near-infrared spectrum absorbing optical filter project supported by TÜBİTAK and conducted by Professor Süleyman Özçelik. The development of inorganic material that absorb near-infrared radiation with a wavelength of 1064 nanometer is important for many optical applications. Lanthanum hexaboride is an interesting material because of its centered absorption spectrum at a wavelength of about between 900 and 1000 nanometers. The spectrum can be redshift by doping with rare earth elements. Why lanthanum hexaboride? Lanthanum hexaboride is a plasmonic metal with a large free carrier density, best known for its impressive thermionic emission properties and low operating function. However, lanthanum hexaboride also absorbs light very strongly at around 1000 nanometer, which falls well within the target range for absorbing solar heat. They have incredible hardness and optical properties of lanthanum hexaboride nanoparticles combined with their high thermal stability. Conventional plasmonic metals, silver, gold, and copper have enormous free carrier density, and when confined at the nanoscale, free electron oscillation result in sharply localized surface plasmon resonance (LSPR) modes. LSPR properties improve light-matter interactions, making these materials ideal for a wide variety of electronic and optical applications. Absorb the most intense radiation hit from the sun, ideally in the range of between 750 and 1200 nanometers. What is plasmonic material? Plasmonic behavior surface plasmon resonance. In other words, surface plasmon (SPR) is an optical phenomenon created by charge density oscillation occurring at the interface of a metal and dielectric material. At the interface between two environments, the collective oscillation of electrons in the metal creates very intense and high electromagnetic fields. That is, the energy carried by photons of light causes mass excitation of free electrons. This energy transfer only occurs around certain resonance wavelength of light. This physical phenomenon is called surface plasmon resonance. Our project for obtaining lanthanum hydroxide material to obtain the lanthanum hexaboride structure. First of all, lanthanum hydroxide structure should be obtained to obtain pure lanthanum hexaboride material by the sol gel method. Lanthanum hydroxide material was first obtained by using lanthanum nitrate, sodium hydroxide, and tergitol. The mixture was incubated at 120 Celsius for 24 hours. It was then left to cool at room temperature for 24 hours. The material obtained at the end of 48 hours was sent to precision washing with distilled water and acetone 5 times for 5 minutes at 3,500 RPM respectively. At the end of the centrifugation process, it was left to dry 1 hour in desiccator at 54 degrees. Thus, lanthanum hexaboride material, which is of the critical importance for the continuation of the project, was obtained as a powder. Structural and analysis obtained lanthanum hydroxide powder were performed. Structural analysis for lanthanum hydroxide. The pattern obtained as a result of APD 2000 Pro XRD analysis of the obtained lanthanum hydroxide material in Gazi University Photonics Application and Sciences and Research Center are given in the figure. Diffraction peaks were observed in the XRD patterns of the films in the 101, 110, 201, 211 planes. This is consistent with the literature data. The peak values obtained in the XRD analysis were obtained in the hexagonal phase of our structure. In the calculations made, the lattice constant A and C has been obtained as a equal to 6.600 angstrom and C 3.84 angstrom. These values are in agreement with the literature values for lanthanum hydroxide structure. Optical analysis, the optical transmittance graph of the lanthanum hydroxide powder sample is shown. Permeability measurements were made with the Burkle brand Vertex 18 model FTIR spectrum located in the Gazi University Photonics Application and Research Center. By measuring the FTIR spectrum, the absorption behavior of the relevant molecules in the between 500 and 4500 centimeter -1 region was observed. The FTIR spectrum behavior of lanthanum hydroxide is compatible with literature studies. Obtain the lanthanum hexaboride material. After the obtaining lanthanum hydroxide, which is one of the important stages of our project, and optimizing its recipe, studies were started to obtain the lanthanum hexaboride material. A recipe was created for the preparation of material. Our experiment takes place at high temperature. Appropriate material have been used. First of all, it was deemed appropriate to use a mole ratio of 1 and 30 between lanthanum hexaboride and boron, and the necessary amounts of materials were into crucible and two materials were pounded in mortar to mix with each other. The resulting mixture was analyzed in the diffusion furnace at Gazi Photonics Research Center at 1000 degrees for 80 hours. Lanthanum hexaboride material obtained after analyzing was kept in acidic solution. It was left to dry and in vacuum desiccator for 24 hours. Obtained in the form of blue powder obtained after the following recipe. Structure analysis for lanthanum hexaboride. The patterns obtained as a result of XRD of structural analysis of the prepared lanthanum hexaboride structure are given in the figure. Diffraction peaks were observed in the 100, 110, 111, 200, 210, 211, 300, 310, 311 planes in XRD models of the planes. The XRD spectrum here is agreement with the studies in the literature data. The crystals, the peak values obtained in the XRD analysis were obtained in the cubic phase of our structure. In the calculation, the lattice constant A equal to 4.12 angstrom was obtained. These values are consistent with the on-powder diffraction standards file number values for the lanthanum hexaboride structure. Optical analysis lanthanum hexaboride. The optical transmittance graph of the powder sample is shown in the figure. The FTIR spectrum of the obtained lanthanum hexaboride is compatible with the literature studies. Results. Firstly, lanthanum hydroxide structure was obtained to obtain pure lanthanum hexaboride material by the Sol-Gel method. Lanthanum hydroxide material was first obtained by using lanthanum nitrate, sodium hydroxide, and tergicol. The XRD analysis of the lanthanum hydroxide material that it had a hexagonal structure and lattice constants were found. It was observed the results compatible with literature were obtained from FTIR analysis. The obtained the lanthanum hexaboride, lanthanum hydroxide, and boron were mixed in a certain ratio and analyzed. In the XRD measurements made, the prepared lanthanum hexaboride sample has a cubic structure the lattice constants of structure which agree with the literature. We are quoting the lanthanum hexaboride material we have obtained on the glass and PET substrate without doping, and we will release the future stage of our project by co-doping elements such as cerium, europium, ytterbium in the raised soil elements to the lanthanum hexaboride material we obtained. Thank you for listening.
Thank you very much, Bushra, for your useful presentation. I think we have a question. Can you see the question now? Bushra, can you hear me?
Yes.
I think we have a question. You can see on the chat section.
I can see. Ben şu an göremiyorum. Hiçbir şey göremiyorum. Ekran gitti.
The question is, what source material you used for synthesis?
We use translate kullanmam gerekecek.
Okay, no problem.
Article in the references. Sesim geliyor mu?
Yeah, we can hear you. You know. I think you showed us.
We use material from Sigma Aldrich. Can you hear me?
Yes, we can hear you.
We use material from Sigma Aldrich and use them as it.
Okay. Okay, thank you very much, Bushra. Now we can pass to Mazha Sayed Muhammad Zadeh. Am I right? From Bilkent University Department of Physics. Okay, you can start.
Okay.
About your talk.
Actually,
and you have 15 minutes from now.
can you see my screen?
Yes.
Yes.
We can.
Okay. Thank you very much. Good afternoon, everyone. My name is Mahsa, a PhD student at Bilkent University. Thank you, the organization committee, for giving me this opportunity to present our theoretical research. Our topic is 2D heterostructures formed by graphene-like zinc oxide and magnesium oxide for novel optoelectronic application. I will talk about vertical heterostructure formed by graphene-like zinc oxide and magnesium oxide. There are two main types of heterostructure. The most common types are van der Waals heterostructure, where there are weak van der Waals interaction between the layers, and interlayer distance are usually larger than lattice constant. Alongside van der Waals heterostructures, recent studies have reported two-dimensional layered heterostructures with interlayer bonding. Interlayer bonding alters the properties of the corresponding single layer. We have investigated both kinds of these heterostructures formed by zinc oxide and magnesium oxide. From the theoretical reports for the lattice constant, as you see here, the lattice constant ZNO and MGO match close match between this that is constant. So and also about zinc oxide, theoretically already fabricated. Presently, layered structure of zinc oxide and magnesium oxide have been utilized in various electronic devices, motivated by several applications of zinc oxide and magnesium oxide monolayer. We considered 4 magnesium oxide, zinc oxide structure of heterostructure in our study. So here, as you see, for example, about AA1 structure, zinc atom here is placed on the top of magnesium atom is placed on top of zinc atom. About AA2 here, oxygen atom is placed on top of Zn atom. About other one, AB1. Magnesium atom is in the center of hexagon of the lower layer, which is zinc oxide, and the other one here. Oxygen atom is in the center of hexagon of the lower layer. So here you can see the relaxed structure. While AA1 and AB1 structures can be considered as van der Waals heterostructures, AA2 and AB2 configurations are bounded heterostructures. So, to investigate the optical properties of these structures, we must know about the stability of the considered system by calculating binding energy and according to mechanical stability condition for 2-dimensional hexagonal lattice. All structures are thermodynamically and mechanically stable, respectively. And also to confirm the dynamical stability of the conserved system, we calculate phonon dispersion. Here, A1 and AB1 configuration have imaginary optical phonon frequency near center of beryllium zone here. But this kind of imaginary frequency might be cleared by effects like temperature, strain, doping, etc. Here you can see some example of them. About AB2, as you see here, has no imaginary phonon frequency and is dynamically stable at 0 temperature. AA2 structure we don't have here because our calculation show that this structure possesses many imaginary frequency and is dropped from the analysis in the rest. Okay. And here we investigate the electronic band structure of zinc oxide and magnesium oxide heterostructures. Here AA1 and AB1 exhibits direct band gap from in the gamma point here. And also the location of maximum valence band and the maximum valence band and minimum conduction band of this structure are same as ZNO monolayer. And about AB2, the structure, the location of this maximum and minimum look like magnesium oxide monolayer. In in all of them, Zn atom, which is red here, as you see, Zn atom has the most contribution in the first conduction band here. And in AA1 and AB1 here, the orbital of oxygen atoms in the ZNO layer form the top of the valence band, which is here, ZNO, oxygen of ZNO layer, Zn green, and oxygen of ZNO layer is, Zn is red and oxygen is green. In the AB2, first valence band here is almost flat, and the main contribution comes from MgO layer. So the top of the valence band is dominated by orbitals of MgO layer. So our conclusion here is this. These results shows that the MgO layer enriched electron collection in the bounded bilayer, and the ZNO layer acts as an electron transverse layer. Okay, up to now, I explained the standard electronic properties of the considered structure at the DFT level. So what about the excited state? At this point, we turn our attention to excited states and excitonic effects for optical properties. We use a single shot of GW approximation approach for the treatment of the quasi-particle effects. The main results are summarized in this table. As you see here, we can see the DFT result. Here is the effect of quasi-particle result, as you see, increased. And here you can see BCE by considering electron-hole interaction. And now here, you can see fat band. The GW band structure are present here. The excitonic eigenvalues can be expressed by the sum of eigenstate of electron hole pair. Here, coefficient A is the coupling coefficient. As you see, coupling is strong at gamma point here. Gamma point again for all of the system. Okay, now to get more insight into excitonic effects, we plotted the normalized absolute value of coupling coefficient. For transition between the top valence band and the minimum conduction band, the coupling is maximum at the center of brilliance, or as you see here, for example, AA1 here, we have transition between 30 and 14. 30 and 14 means that 30 shows us maximum of the valence band. 14 means minimum of the conduction band. So as you see here, coupling coefficient, coupling is close to the center of the brilliance zone here, for example. And now we have a good result here. We calculate also imaginary part of the dielectric function by using DFT, GW, and BC. As you see here, DFT is light blue, GW red, and BC blue. As you see, by using, for example, AA1 structure, AA1, this is DFT results. By using GW, by considering quasi-particle effect, as you see, the band gap in reach here, as you see, from here to here. Okay, and after that, by using the Bethe-Salpeter equation, the first peak is placed at the middle of light spectrum, visible light spectrum. Okay, and here in both of them, AA1 and AB2, first peak of BCE is at the middle, and about AB2, first peak of BCE is appears near the violet light. Another important issue here is the position of the dark exciton. Our results show here, for example, first one about AA1, first yellow shows, and here the circle, this circle shows dark exciton, but around yellow circle we don't have this empty circle. About AA1 and AB2, and about AB2, the first dark exciton here, the first dark exciton empty circle appear near the third base eigenvalue, which is purple here. 1, 2, 1 is red, sorry, 1 is yellow, the second is red, and the third one is purple. So dark exciton is close to the third base eigenvalue. Okay, so as a conclusion, we studied the mechanical electronic, and optical properties of 4 possible heterostructures formed by zinc oxide and magnesium oxide monolayer, and AA1, AB1 can be considered as van der Waals heterostructures, and there is interlayer bonding in AB2 structure. Bound structure calculations based on DFT show that the orbitals of zinc atom dominate the first conduction bond of this structure. The MgO layer orbital dominates the top valence band of AB2 structure. And applying GW calculation show a strong oxidon effect in MgO's dendrite structure. And I'm not able, okay. Our results shows that the optical band gaps of these structures are in the visible light spectrum, which is a very important result for us. Thank you very much. I just want to thank you for my professor, Oğuz Gülsaran. If any question, thank you.
Okay, thank you very much. Masa, we can take the questions.
Okay. I don't see any question.
Yeah, I also don't. I think there's no questions. And thank you very much.
Thank you.
We can. We have the last speaker, Dr. Halil İbrahim Epikere.
Hello.
He's from Gazi University Photonic Application and Research Center. And you can start about your talk.
Okay, thank you very much. Can you see my presentation?
No. We
No.
couldn't. No.
Sorry.
No problem.
Let me try again. So, can you see now?
Yes.
Okay, thank you very much. Hello, everyone. Dear participants, first of all, I would like to greet you all with respect. My name is Halil İbrahim Epikere. I'm researcher at Gazi University Photonic Application and Research Center since 2010. Now, I will try to give you my presentation titled Investigation of the Effect of Annealing on the Structural and Optical Properties of RF-sputtered tungsten oxide nanostructures for memory store applications. So the motivation, the development in CMOS and flash memory technologies in electronics in the last few decades have greatly affected the whole world. So memory store, which have been put forward a promising device for both memory device and neuromorphic device that mimic the structure and functioning of the brain, have made it even more interesting. So our motivation is in this study is to determine the structural and optical properties of tungsten oxide material, which can be used for the memory store device, which is defined as a passive circuit element in the electronics by successfully producing the magnetron sputtering technique. Firstly, if we try to define the term memory store, the memory store theory was put forward in the 1971 by Leon Chua, a professor in the Computer Science and Electrical Engineering Department at the University of California. Professor Chua had observed the models of capacitor, resistor, and the inductor, and he observed the missing part, which is named as memory store or memory resistor. The practical representation of this memory resistor was expanded in 2006 by the HP scientist Stanley Williams. This technology was discovered more than a few decades ago, although it got made up in recent times. We know that every electronic circuit can be designed by using several passive components, namely resistors, capacitors, as well as inductors, but there will be an essential fourth component, which is termed as memristors. So these are semiconductors used for the jointing passive components to form a fourth component, and the resistance is named as memristance. It is a resistance. Memristor is a resistance. So it depends on charge in memory circuits. So the resistance unit is, we can see here, ohm. So we can see here the memristor structure physically developed by HP researchers in the figure. So if we look figure A, we see the oxygen-poor titanium oxide layers as the upper layer, and the bottom layer of this structure, there is a full stoichiometric titanium oxide layer. Oxygen vacancies in the upper layer are spread into the upper layer. If a positive voltage, like figure B, applied, if a positive voltage applied to the system, to the structure, it causes positively charged oxygen vacancies charged to the layer dragged into the insulator layer, going to the down. This mobility shifts the boundary between the insulating and conducting layers towards the lower metal contact, causing the expansion of the upper titanium oxide layers and hence the expansion of the conductivity region of the whole structure. The increase in the conductivity of the device is directly proportional to the increase of the applied positive voltage. Samely, like figure C, a negative voltage to be applied to the device attract positively charged oxygen vacancies through the upper titanium oxide layer. So in this case, the insulating and the resistivity titanium oxide layer will expand and the insulating will increase throughout the device. So therefore, as the applied negative voltage value increase, the conductivity will decrease proportionally. That is, in general, when current flow through a memristor in one direction, the the system resistance will decrease, and when currents flow into the opposite directions, its resistance will increase. Since there is a material movement here in the structure, the oxygen vacancies movement, the system will remember the last resistance value when the electricity of the circuit is cut off and charged again. So our main material, tungsten oxide here, let's look at the superior properties of the tungsten oxide material in the metal or metal oxide form. We can see some properties of tungsten. Due to the tungsten oxide high melting temperature, photoelectrochromic properties, toughness, and the mechanical properties, it is considered a potential candidate for optical and electrical applications. So tungsten oxide can be obtained by many methods, such as thermal oxidation, some chemical synthesis method, and the method we used, magnetron sputtering. Also, tungsten has a wide band gap value between 2.6 electron volt and the 3.4 electron volt. And depending on its stoichiometry, tungsten oxide can exhibit insulator, semiconductor, or even metallic properties. And samely, depending on the production method and the production conditions, tungsten oxide can have many atomic configurations, like monoclinic, tetragonal, triclinic, hexagonal, cubic, and orthorhombic. So in this study, we investigated that the production of calibration samples tungsten oxide material, which is the promising material for memristor device, and the determination of its structural and optical properties. So we can see some of experimental systems we use in this research. And okay, the position of the tungsten oxide thin film samples. We were used RF magnetron sputtering technique to deposit the tungsten oxide thin films on our silicon substrates. The parameters used during the coating, such as phase pressure, coating pressure, argon-oxygen ratio, or and the power, etc., are seen here. In order to determine these parameters, many calibrations were made beforehand. These values were used for the final coatings, final deposition. After the deposition, we do some structural analysis and optical analysis. For structural analysis, SEM-EDS, XPS, and XRD analysis were performed. For the optical analysis, UV visible and the photoluminescence analysis. So firstly, SEM-EDS analysis was performed to determine the stoichiometry of the tungsten oxide structure we deposit. Here we have given the results obtained from the stoichiometry analysis performed with SEM-EDS technique. So according to these results, peaks at 0.5 kiloelectron volt and the 1.8 kiloelectron volt values, which also refer presence of tungsten and oxygen in our structure. So according to our SEM-EDS results, oxygen-tungsten ratio in the structure is approximately 3, calculated value, of course. So after the SEM-EDS analysis, we performed XPS analysis on the same samples for stoichiometry detection and the elemental analysis. According to the XPS results obtained, the oxygen-tungsten ratio in the structure was calculated 2.88. So this ratio was found by dividing the areas under the oxygen and tungsten peaks. So these results are consistent with the XPS results of tungsten oxide structures produced by some other techniques in the literature. After the XPS analysis, here we see the results of another structural analysis, XRD. So XRD analysis were performed both for samples coated and the annealed coated samples named as deposit and the annealed samples at different temperatures. According to our XRD results, the 200 peak, which becomes more intense and sharp with increasing annealing temperature, is the strong diffraction peak for all temperatures. So for tungsten trioxide or tungsten oxide material, crystallization started at approximately 500 Celsius centigrade degree, which supported to the literature. So it was observed that the crystallinity of tungsten oxide thin films produced at room temperature changed to a better form with increased annealing temperature. As we see XRD results as deposited and the annealed samples at 300 centigrade degrees, our samples structure are still amorph, but when the getting higher temperature like 400 Celsius degree, it's starting crystallization. So after the structural complete the structural analysis, optical analysis of samples were carried out. So our optical analysis techniques applied for our samples, we talked before, UV visible and the photoluminescence. So we performed the UV visible analysis, determined the band gap values of the samples we prepared. As usual, the band gap calculation for transparent material from the UV visible calculated with tag plot. But for opaque and the matte materials, band gap values can be found by using the result of reflection analysis from UV visible and the Kugelkamun theorem. So since we coated our samples on silicon substrate, so it's the matte substrate, we calculated the band gap values of our samples using Kugelkamun theorem for our reflection results. So here we see the band gap values of our samples. It can be seen, these results, that the band gap values decrease almost regularly with the increasing annealing temperature. So another optical analysis is the photoluminescence analysis, where performed also are sampled. The main peak from the photoluminescence results correspond to the bandgap values. It was observed that the bandgap values found to be consistent with the UV visible shifted to the left with increasing annealing temperature, and the peak intensities also increase. So peaks occurring outside the main peaks, these peaks I'm talking about, are localized states caused by the presence of oxygen vacancies or defects in the nanostructure. The green emission peak can be attributed to the different luminescence center, such as imperfect energy level caused by the tungsten vacancies and oxygen vacancies, and the dangling bonds of our samples nanocrystals. So we see the table, the comparison of bandgap values obtained from UV visible and the photoluminescence analysis. As can be seen, the bandgap values obtained with the both techniques are close each other. The bandgap values decrease with the increasing temperature we can see also here. So we published these studies with our research group in a journal indexed in Science Citation Index. So you can find more details, information, the subject by accessing our article and conclusion. So all of these results highlight that the tungsten oxide nanostructure, which is deposited suitable stoichiometry, and annealed can be used as an active layer in electronics and optoelectronics device applications. So these results also can be useful data on the reactively coated almost completed stoichiometric tungsten oxide layer and oxygen-poor tungsten oxide layers during the fabrication of memory-stir device. So for the memory-stir device, the situations where the structure are in more crystalline form are preferred. As a result of the experiments we have done, we recommend the researchers anneal the tungsten oxide thin films 400 centigrade degrees as the annealing temperature. That's the crystallization begins point. So this temperature can be sufficient for the ionization of the metal subcontact to be selected and can be accepted as a beginning of the crystallization of the tungsten oxide structures. Apart from this, maybe as a suggestions for the future research, the increase in the annealing temperatures can be tried with the 50 Celsius degrees increments instead of 100 Celsius degrees temperature. So thus, metal with the lower ionization temperature can be more closely matched to the temperature at which tungsten begins to crystallize. After, of course, with all the researchers, after our presentation, we can share our studies on metal and top and bottom contact material can be used for tungsten oxide memory-stir device with the research who wants. And reference. So I want to thank all my colleagues for supporting me with this research. And so thank you for all listening to me.
Okay, thank you very much, Halil İbrahim. Okay, this was our last speaker, and we finish our session. And we will have a around 10 minutes break. Then we will meet again. Thank you very much.
Thank you very much.
Hello, everyone. This is last session of the conference. I hope you had a pleasant time on the light science and light technology during these 3 days. It's nice to be with you. We, as the Gazi Photonic family, wanted to welcome you well. I believe the next year we will be able to hold this conference face-to-face, and we will drink a Turkish coffee together. Thank you again, and let's start this session. Okay. I'm sorry. I want to say something. I also want to remind you, after the end of this session, we have closing ceremony. Please join it, and we will also announce the best 3 speaker presentations there, young speaker presentations. Okay, now we can start. We have 8 speakers on this session. Firstly, we will start. An invited speaker is Associate Professor Güven Turgut from Erzurum Technical University, Erzurum, Turkey. I would like to briefly touch on his work. His major research interests are 2-dimensional materials, thin films, photonic materials, and devices. He has published more than 70 research papers, and his works have been cited more than 2,000. And his title of talk is Optimizing CVD Growth Parameters of Indium Selenide Monolayers. Okay, I leave the microphone to Associate Professor Güven Turgut. Please go for it. Are you ready?
Yeah, I'm ready.
Okay.
Thank you very much. I am Güven Turgut from Erzurum Technical University. Firstly, hello everyone. I will give a speech about optimizing CVD growth parameters of indium selenide monolayers. Firstly, I will give a content of my speech. Firstly, I will start from what is the 2-dimensional materials, what are their properties. Then I will start to give more detailed information about indium selenide material. Then I will give some experimental detail of our research group. Then I will talk about the results. And what is 2-dimensional materials? We know 2-dimensional materials have gained an important attention after discovery of graphene. 2-dimensional materials actually refers to a single or a few layer of atoms, and these materials can be a single material on top of some surface, and they can be more layers. And when we classify these materials according to their conductivity types, and you can see here insulator, semiconductor, and semi-metal or superconductor materials. And firstly, we know the graphene is the most important 2-dimensional material because it has been discovered firstly, and graphene is composed of the carbon atoms on hexagon form, and graphene has very interesting properties such as high electrical conductivity, high mechanical durability, and hardness. But graphene doesn't have any band gap. Because of this, the material research community wants to discover other two-dimensional materials like semiconducting materials, because when you work on the semiconductor material, you can control their properties easily. Then one of these two-dimensional material is indium selenide. What is indium selenide? I will give some detailed information about the indium selenide. Indium selenide actually has many compounds according to indium and selen ratio on this material. First of them is indium-1, selenium-1 material. This stoichiometric material is a two-dimensional one. And second one is indium-2, selenium-3 material. This material is also a two-dimensional one. And you can see here there are lots of compounds of indium and selenium. And one of them is indium selen 121. This material has also 3 different polytypes. These polytypes are epsilon, beta, and gamma. These polytypes are classified according to their stacking order of this material. And we actually work on the indium selen epsilon phase here. In this phase, you can see here the crystal structure of these materials. When we see the top view of these materials are M2X2 structure. You can see top view here. You can see the hexagon of this material, and then you can see the 2 layers of indium selen. And when you see the 1 layer of indium selen material, you can see you have 2 indium and 2 selenium atoms here. And for the last picture shows the bond distances of indium between indium and selen, or indium and indium atoms. You know, the indium selen material is a two-dimensional material. You can find this material in a form of monolayer or bulk form. When you go from bulk structure to monolayer, you can see the quantum effects for this material. The band gap, the electronic band gap changes from direct to indirect for this material, and band gap value is also increased from 1.39 eV to 2.84 eV, and you can see on this picture here. This is because of the layers interactions for these materials. And for these materials, the effective mass of the carriers is very light, is around the 0.14 M0, and the carrier's mobility is very high. Because of these properties, this materials has a fast switching property, high on-off current ratio, and the mechanical flexibility is very good for this material. These properties open the wide range of potential application for this material. And then I will talk about our experimental stuff here. We did many experiments on these indium selen materials here. We used the CVD system to deposit indium selen two-dimensional or monolayer indium selen material here. You know, the CVD is actually chemical vapor deposition. We use this experimental stuff here. In CVD, you can see some stage of deposition, some deposition stages here. Firstly, your source powder will evaporate, then it will transport to substrate with or via carrier gas. Then it will have a diffusion to substrate, and there will be desorption on absorption on the substrate. Then the other stuff of CVD will be going out. Then we use the precursor materials here, indium-2 oxygen 3, but you can use indium, metallic indium, or indium selenide, or indium iodide. Then we use the substrate here, mica, silicium oxide, and sapphire substrates. Firstly, we try to determine some precursor amount or some salt concentration or salt type for this material. When you deposit some TMDC material, you can use some salt, for example, NaCl, KBr, etc. When you use these salt materials, you can reduce the melting point of your precursor, and you can increase the flake size of TMDC materials. Because of this, we wanted to use some salts to decrease the indium-2 oxide 3 precursor melting point. And when we used these salts, we didn't see any indium selenide related material here. Then we try to make an experiment only using KBr or NaCl salts, and we saw very interesting results here. You can see we saw some triangular shapes, and they contain only salt materials, KBr or NaCl. Then we try to use low vacuum equipments, and we did our experiments under 50 torr pressure. Then we started to try optimization of temperature of selenium powder. When we do this, we use the single zone split furnace here, and if you want to change any powder temperature zone, you can move your powder position. And we did this for selenium. We used selenium in a gas flow site, and selenium distance from the center of the split furnace is from 16 to 18 centimeters. And when we use these distances, and we saw some triangular shapes for 16.5 and 17 centimeters. Then we try to we optimize this 17 centimeter distance for this material. Then we start to try the other parameters for precursor amount. When we when we change the precursor for this material, we changed precursor amount from 5 mg to 12.5 mg milligrams. Mg means when we use the low precursor amounts, we didn't see anything about indium selenide, or when we increase the indium 2 oxide 3 precursor than 10 milligrams, we didn't see any good shapes of indium selenide. Then we optimized this 10 milligram precursor amount. After these parameters, we try to optimize gas flow rate and gas ratio. We used argon and hydrogen gases here. We firstly used the total gas concentration 80 SSEM, and then we tried to change this gas ratio. First, we used the 70 SSEM argon, 10 SSEM hydrogen. Then we use 60 SSEM argon, 20 SSEM hydrogen. Then we use the 50 SSEM argon, 30 SSEM hydrogen. When you use this ratio, we saw the best ratio is 1. Actually, yes, 25% hydrogen rate is the best result for us. This rate is according to total gas. When you use the low concentration of hydrogen, maybe you couldn't reduce the indium to oxygen 3 to make indium to make a bond formation between indium and selenium. If you use more hydrogen, and you can maybe sweep the indium selen stuff on top of the substrate. When we decide to the best gas flow rate, gas flow ratio for this material, then we try to optimize the total gas flow rate for this material. Actually, when we try to this flow rate, we saw our 80 SSEM gas flow rate is the best result for us. When you use the very low concentration of gas, maybe you can increase your flake size, but we didn't see it lower than 80 SSEM. But when we increase your total gas, you can increase the nucleation number of your material. But we saw the 80 SSEM, the total gas is the best for our results. The last experimental stuff is the confinement experiment. We did these confinement things by using the 2 mica substrate on top of them. When we use this one, we confine the precursor of indium and selenium. We confine these materials on a very small area, and the distance between 2 mica substrate is around 150 micrometer. And when you confine this precursor materials vapor, and two different effect is is dominant here. One of them is the nucleation size, nucleation number of for your material will be reduced, and second one, your lateral growth will be increased for this material. And you can see here, when you use the confinement area, you can increase the size of two-dimensional materials. When we do this, we increase our flake size from 15 micrometer square to 200 micrometer square by using this experiment. As a result of this, our studies, we saw indium selan monolayers. Here you can see here AFM result. We measure the thickness. Our monolayer is around 1 nanometer, and you can see the Raman spectra for these materials. When we go from bulk to monolayer, we can see the decrease in the Raman intensities of our material. And we also saw some other phases of these materials when we change the gas flow rate of hydrogen for these materials. And interestingly, when we saw some hexagon things, these are the mixed phases of indium-2, selenium-3, and indium selan. We did this by changing the hydrogen concentration, and also we can see the bulk or 3 or 2 layer Raman spectra or AFM spectra. Yes, thank you very much listening me, and this is my talk about optimizing some CVD parameters of indium selan. And if you have questions, I can answer them.
Thank you very much for your nice presentation.
Thank you.
Are there any questions? I'm waiting 2 shorts, please. If you have questions, I will check the screen.
I'm checking also the screen now.
Yes, I think no questions. Okay. Thank you again, and I also personally thank you because you chaired the previous session and supports us, Dr. Turgut. See you next year, face-to-face, hopefully. Thank you very much.
You're welcome.
Okay. And now let's move on to the next talk. Malika Tuzelbay from Al-Farabi Kazakh National University, Kazakhstan. Her title of talk about statistical pattern of exoplanets. Are you here, Malika? Can you hear me? Yes. We cannot see anymore. Okay, now is good. Please, your turn. Are you ready? Can you share the screen? Yes, it's good. Yes, already. Okay. Yes, look very well. Microphone is yours.
Lecture 2 is about statistical properties of exoplanets. First of the study, description of general statistical properties of exoplanets. And the object of research is exoplanets. And the relevance of the study promotes a deeper understanding of the origin and evolution of planetary systems. Task on the work. First, issue a certificate of methods of searching for exoplanets. Second, consideration of exoplanets that may be the search of life. Third, determination of the current number of exoplanets. What is an exoplanet? Within an exoplanet, an object with any planetary mass outside the solar system. The mass of the object must be large enough to have a spherical shape. Objects with a small mass are called exocomets and exoasteroids. You can see moons, dwarf planets, exoplanets, brown dwarfs, such, and they can see radius and the mass. This function is mass for Kuiper belt object with a number and the mass. Central proxima. The planet is very close on a 4.2 light year from us. The planet receives about 65% of the light that the Earth receives from the Sun from its star. Theoretically, there could be life on this planet, but if this is the case, then in 2017, living right here. This flash exceeds the usual light by 1,000 times. And you can only survive such an epidemic if hide deep underground. Some types of bacteria had little chance of salvation. It's worth exploring the planet, but with the help of robots, there is not a point in creating a colony here, because a catastrophic situation can happen again at any time. And this rose 128b. The planet may be suitable for life. One disadvantage is that its mass is 1.5 times that of the Earth. It's slightly closer to its native star than to its former exoplanet. A full cycle a year, respectively, the planet does in just 10 days. The temperature here, according to preliminary calculation, can vary from 0 to 20 Earth temperature. In new study, this is brown dwarf. This name and the image taken from the Cake-2 telescope. The mass of a brown dwarf is equal to mass 30-40 Jupiter. At conclusion, first we discovered 400,966 exoplanets and 5,243 planets are candidates for exoplanets. Second, the number of exoplanets in the Milky Way galaxy is 100 billion. Third, planets such as Earth have been identified 20 billion. Fourth, we contact the graph of the mass dependence of radius of exoplanets. Fifth, we have created the mass function of exoplanets. That's all. Thank you for your attention.
Okay. Thank you so much, Malika. Dear participants, if you have question, you can ask directly on the chat screen, please, or raise your hands, maybe. Okay. Okay, no questions. Thank you again, Malika. See you. And now it's time for next speaker, Dr. Meltem Dönmezkaya. Meltem is a member of my research group. She is from Gazi Photonic, Ankara, Turkey. Her talk's going to be fabrication and characterization of molybdenum disulfide heterojunction structure. Yes. Yes, you like very good. Please go for it, Meltem. Are you?
Hello, everybody.
If you're ready, you can share your screen and microphone is yours.
Okay. Welcome to third ICLLT conference. My name is Meltem Dönmezkaya. Okay, sorry. I am working in the Surface Analysis Laboratory at Gazi University Photonic Application Research Center. Also, at the same time, in addition to our research, I give training to our students. Today, I will make presentation titled Fabrication and Characterization of Molybdenum Disulfide Silicium Heterogeneity Structure. Why did we choose molybdenum disulfide materials? Firstly, it is interesting and promising material among the transition metal decalcogens family. Secondly, it has unique electronic and optical properties. Also, since the light absorption of these materials extends from visible to near-infrared spectral region, there has been a lot of work recently in the development of optoelectronic devices. There are applications areas such as optical sensors, chemical sensors, photodetectors, solar cells, energy storage devices. We are dealing with photodetector and solar cell applications among them. Focus of this work. Molybdenum disulfide thin films was deposited successfully by sputtering system. Analysis of produced films were performed with various characterization techniques. Then molybdenum disulfide P-type silicium device fabrication was carried out for optoelectronic device applications. Fabrication was done as follows. 400 nanometer thick gold electrodes were deposited on the produced films. Deposition of molybdenum disulfide thin films were performed by sputtering system. Deposition parameters are presented in the table. Thickness set at 100 nanometer. Substrates are silicium dioxide, coated silicium, P-type silicium, and Corning glass. Substrate temperature is 600 centigrade degree. Structural properties of films were analyzed with XRD and XPS system. Surface morphology of films were investigated by AFM system, and optical properties were analyzed UV visible spectrometer and FDR spectrometer. And then molybdenum disulfide P-type silicium heterostructure fabrication was performed for optoelectronic device applications. After fabrication, IV measurements were carried out in dark environment under infrared light at room temperature. XRD analyzes exhibit characteristic 002 diffraction peaks for all the samples. These diffraction peaks in the pattern can be indexed to the hexagonal structure of molybdenum disulfide. XPS was used to explore the chemical bonding states of molybdenum, sulfate, and oxygen. Both survey spectra show the presence of molybdenum, sulfate, carbon, and oxygen in the produced films. That is, XRD and XPS results show that molybdenum disulfide film was successfully formed. Morphological analysis of films were performed by HBAFM system. 3 square micrometer surface area was scanned. Obtained images have presented as 2-dimensional at 3-dimensional. It was determined from the results that surface of all films were homogeneous. It was observed that the surface of molybdenum disulfide film deposited on P-type substrate had less roughness. To evaluate optical properties of molybdenum disulfide films, transmittance, reflectance, and absorbance spectrum were obtained by UV visible spectrometer. It was determined that film had good light absorption in the measured wavelength range. Also, the band gap value was found to be 1.5 electron volt. The FDR system was used to examine optical properties of the films in the wavelength range of between 1 micrometer and 2 micrometer. The highest absorption and transmission were seen in molybdenum disulfide film deposited on P-type silicium substrate. When all characterization results were examined, molybdenum disulfide-based heterojunction fabrication was performed using molybdenum disulfide film deposited on P-type silicium, which was determined to have low roughness, homogeneous surface, good transmission and absorption. The test of produced device were carried out with the IV measurement system in the dark and under the infrared light. As a result of it was determined that device was sensitive to near infrared light at 780 nanometer wavelength. And then the electrical properties of the produced heterojunction device were investigated with 3 different methods. These methods are classical thermionic emission theory, Nord method, and Cheung method, respectively. The electrical parameters are demonstrated in the table. Ideality factor, barrier height, and series resistance parameters of the fabricated device were found as 1.98, 0.529, and 280 ohm, respectively. As a result of the sensitive or produced device to near infrared light was observed, also fabricated molybdenum disulfide-based heterojunction device exhibited good rectification performance. This study showed that the produced device is suitable and promising for molybdenum disulfide-based optoelectronic applications. In addition to this work, we have successfully produced molybdenum disulfide P-type heterojunction solar cell with cheaper and higher quality electrode production using the aerosol jet printing system for the first time. We propose that the photovoltaic efficiency of molybdenum disulfide-based solar cell will be increased. We are currently awaiting the publication of this work. Thank you, Photonics family. Thank you for listening.
Okay, thank you very much for your nice presentation. Are there any questions to Meltem? I will check. Thanks, Dr. Meltem. Nice presentation. Thank you. Are there any questions? Okay, Meltem.
Thank you.
I think no questions.
Good evening. Good ceremony.
Okay, see you on coffee break face-to-face, I guess. See you, bye. Okay, this session is going to a little fast, but there will be no change in the closing ceremony time. It is time on quarter to 8 because there are people who will join directly on this session. I want to remind you. And now I would like to invite next speaker, Zihila Alipana. Sorry for my pronunciation, Zihila, from University of Tabriz, Iran. The title of talk role of UV absorbers on the IRLD spectra of liquid crystal network polymer. Are you here, Zihila? I cannot see screen. We have a video. Okay.
Hello.
Video. Okay.
I'm Jilali Pano from University of Tabriz, Tabriz, Iran. I'm going to start my presentation with title Role of UV Absorbers on the IRLD Spectra of Liquid Crystal Network Polymer in third International Conference on Light and Light-Based Technologies. The industrial world is changing day by day as human society prepares to enter a new generation connected with the fourth industrial revolution. The market for the fourth generation, the market for the business of the fourth generation was $86 million in 2020, and it's expected to grow to $267 million by 2026. The focus of this generation is on automation of traditional manufacturing, modern smart technology, machine-to-machine communication or M2M, Internet of Things or IoT, and smart machines, that all of them without the need for human intervention. Smart materials are required for this purpose. These materials are part of a class of materials that may respond to environmental changes in order to adapt to their surroundings. The features of these materials can be altered in this fashion, and the majority of the modifications stated occur in their shape and size. It's worth noting that there are a variety of external stimuli, including electric and magnetic fields, temperature changes, chemical reactions, and light, with light receiving the most attention because it's a renewable and easily available energy source that's also cost-effective and can be controlled remotely. In this regard, light-sensitive materials are needed among the available. Light-sensitive polymers play a key role. These polymers in turn have a variety of types that are selected according to the specific application. These groups including photo-induced enrichment polymers, photoisomerization, photo-induced cross-linking polymers, photo-cleavage, and photo-induced energy conversion. That liquid crystal network, or LCN, which investigated in this research, is mostly used to design and manufacture light-actuated actuators, which can transfer energy of light into mechanical quantity. These polymers, in turn, has led to development of various industries such as soft robotics, sensors, and medical industry. The polymerization of monomeric components called reactive mesogens was first produced in 1965 as a way to make liquid crystal polymer. Reactive mesogens are split into two groups, acrylate and diacrylate, which are employed to make liquid crystal networks of the diacrylate group. After polymerization, the structure is virtually completely cross-linked. Meanwhile, research into these materials based on inferences from their Fourier transfer infrared spectra, FTIR spectra, is critical. Because the most common uses FTIR most common uses in the identification of unknown materials and confirmation of production materials. The information content is very specific in most cases, permitting fine discrimination between like materials. The split of FTIR analysis makes it particularly useful in screening applications, while the sensitivity empowers many advanced research applications. When looking at IRLD spectra or allied dichroic spectra, you may learn a lot about the structural order and orientation of the functional groups in the polymer network, because each of the functional groups in matter exhibits absorption in a specific range of IR spectra. However, as previously stated, the influence of UV absorbers on the IRLD spectra of the liquid crystal network polymer was examined in this research. The chemical structure of the utilized UV absorbers in this slide has been drawn, with all of them selected from the Tinovin group to allow for the most precise analysis. In this regard, Vertex 7 NFIR spectrophotometer was used for recording vibrational spectra over a wave number, mentioned wave number range, which combined with a KRS5 polarizer and cell temperature controller. IRLD spectra for the examined LCN polymers, where LCN1 contains tinovin type 1 and LCN2 contains tinovin type 2, are shown in the slides. It's worth noting that all of the relevant liquid crystal networks use the same reactive mesogen. In here is RM82 and potentiator with the same percentage of weight. The only difference is the type of tinovin. As can be seen, the amount of absorbance at 0 and 90 degree of polarized IR wave differs dramatically in two of these LCs. Also, the mentioned tips are available for LCN3, which contains tinovin type 3. The differs can be seen in this figure. Following the calculation of the dichroic ratio, it was possible to perform a more accurate analysis. In all of the studied liquid crystal network polymers, the functional groups C, single bond C, COC, and CO are oriented in planar. This is the case if the orientation of the functional groups aromatic ring, C double bond O, and CH2 is homotropic. However, a detailed examination reveals that tinovin type 1 has a greater effect on the planar orientation of the mentioned functional group specified than other tinovins. Tinovin type 3's influence on the homotropic orientation of the remaining functional groups listed in this table has also outperformed that of others. The reason for these differences is that the intermolecular interactions between tinovins, between utilized tinovins and utilized reactive mesogen are not same, because the size and chemical characteristics of used tinovins are not the same, and consequently the intermolecular interaction and the resulting effects will be different. Thus, through this technique, it's possible to select the type of UV absorber or ultraviolet absorber according to the desired application. Thanks for your attention.
Okay, thank you. Now it's time for a coffee break. We take a break for 30 minutes. Then we'll listen to 4 speakers more, and finally we will have the closing ceremony. Please don't get lost. Now you can watch our promotional videos. See you again.
the meeting point of the roads between Europe, Asia and Africa, and a perfect interweave of cultures, Ankara, a culture paradise of 5,000 years. These lands, which hosted many Western and Eastern civilizations, became the center of the Turkish War of Liberation, launched with the downfall of the Ottoman Empire, and became the capital of the Republic of Turkey. You can find the opportunity of treading the path of history by visiting the year-round open museums and open-air museums in Ankara, which serve as a bridge between past and present, remaining intact, defying thousands of years. There are many historical and modern mosques in Ankara. The roof of Hacı Bayram Mosque was built in such a way as to embrace the wall of the Temple of Augustus, as if to prove the centuries-old coexistence of religions in fraternity. You should never depart from Ankara without seeing the traditional Ankara houses. Ankara is also one of the most important stops on the historical Silk Road. The inns, caravansarais and traditional bazaars of that period provide a safe transport, easy access and a wealth of purchasing opportunities. Historically important Turkish baths and spas are the health and tourism sources of Ankara. Ankara is also a university city, boasting 5 big state and 10 private universities. Ankara is also a city of art, life and entertainment. The state opera and ballet performances, the plays staged by the state and private theatres, the concerts by the Presidential Symphony Ankara is the easiest city in terms of transport. Ankara is also easily accessible by air, land and rail from any country in the world. The Turkish cuisine is one of the world's most famous cuisines. The Ankara specialties constitute the select examples of Turkey's culinary marvels. Ankara is the homeland of the Ankara goat, the source of clothes vying with silk for quality, the Ankara rabbit, whose wool is as light as Angora wool, the world-renowned Ankara cat, and the flower of love, also dubbed the flower of the prophet. Its shopkeepers, the carriers of a tradition of 1,000 years ago known as Ahilik, the Guild of Turkish Craftsmen, are sincere and hospitable. They are generous, alms givers, and like guests, with their tables open for everyone. They are, in short, humanists. Ankara, of which Atatürk voluntarily became a fellow townsman, is a monument of peace, with its cultural foundation and a center of tolerance. With its history and natural riches, eating culture and tourism, agriculture and animal husbandry, its politics, sports people, art, and its residents is a leader capital breathing life into Turkey. A culture of paradise of 5,000 years. Ankara, the heart of Turkey. the meeting point of the roads between Europe, Asia and Africa, and a perfect interweave of cultures, Ankara. A culture paradise of 5,000 years. These lands, which hosted many Western and Eastern civilizations, became the center of the Turkish War of Liberation, launched with the downfall of the Ottoman Empire, and became the capital of the Republic of Turkey. You can find the opportunity of treading the path of history by visiting the year-round open museums and open-air museums in Ankara, which serve as a bridge between past and present, remaining intact, defying thousands of years. There are many historical and modern mosques in Ankara. The roof of Hacı Bayram Mosque was built in such a way as to embrace the wall of the Temple of Augustus, as if to prove the centuries-old coexistence of religions in fraternity. You should never depart from Ankara without seeing the traditional Ankara houses. Ankara is also one of the most important stops on the historical Silk Road. The inns, caravansarais and traditional bazaars of that period provide a safe transport, easy access and a wealth of purchasing opportunities. Historically important Turkish baths and spas are the health and tourism sources of Ankara. Ankara is also a university city boasting 5 big state and 10 private universities. Ankara is also a city of art, life and entertainment. The state opera and ballet performances, the plays staged by the state and private theatres, the concerts by the Presidential Symphony Orchestra, as well as national and international festivals keep its people occupied for a whole year. Seymens. The swashbuckling heroes and traditional dancers from Central Anatolia may show up in all corners of Ankara. All institutions and organizations complying with Atatürk's motto, sound mind, sound body, have spearheaded the construction of many sport halls in Ankara. Ankara also draws attention with its parks and recreation areas. It is located at the heart of many of Turkey's tourism riches. Ankara is the easiest city in terms of transport. Ankara is also easily accessible by air, land and rail from any country in the world. The Turkish cuisine is one of the world's most famous cuisines. The Ankara specialties constitute the select examples of Turkey's culinary marvels. Ankara is the homeland of the Ankara goat, the source of clothes vying with silk for quality, the Ankara rabbit, whose wool is as light as Angora wool, the world-renowned Ankara cat, and the flower of love, also dubbed the flower of the prophet. Its shopkeepers, the carriers of a tradition of 1,000 years ago known as Ahilik, the Guild of Turkish Craftsmen, are sincere and hospitable. They are generous, alms givers, and like guests, with their tables open for everyone. They are, in short, humanists. Ankara, of which Atatürk voluntarily became a fellow townsman, is a monument of peace, with its cultural foundation and a center of tolerance. With its history and natural riches, eating culture and tourism, agriculture and animal husbandry, its politics, sports people, art, and its residents is a leader capital breathing life into Turkey. A culture of paradise of 5,000 years. Ankara, the heart of Turkey. the meeting point of the roads between Europe, Asia and Africa, and a perfect interweave of cultures, Ankara, a culture paradise of 5,000 years. These lands, which hosted many Western and Eastern civilizations, became the center of the Turkish War of Liberation, launched with the downfall of the Ottoman Empire
Hello again. This is last part of the final session. Now it's time for the next speaker, Hicret Hopoğlu from Sivas Cumhuriyet University, Turkey. Her talk's going to be dependence of film thicknesses on the XRD and AFM and transmittance properties of nickel oxides. Please, your turn. You have 15 minutes, Hicret. Okay, can you share your screen, please?
Okay.
Okay.
Thank you.
We cannot see your presentation yet.
Nereden paylaşıyorum?
Maybe please click screen share on the bottom line. Yes.
One minute.
Okay, no problem. We cannot see your presentation. Maybe firstly, okay, okay. Yes. But this is not your presentation, I think.
One minute.
Is your PowerPoint open? Your no problem. We will wait you. We have time. Don't worry. Hicret Hocam, aynı şekilde oluyor.
Evet, açamıyorum.
Panik yapmayın. Sanırım PowerPoint'iniz açık değil sizin şu an.
Arkadan mı açacağım hocam?
Önce PowerPoint'inizi açar mısınız?
Tamam. Hemen açtım.
PowerPoint'iniz açık olsun. Ondan sonra share screen, ekran paylaşımı yapacaksınız.
Tamam.
Oraya gelecek ekran paylaşımı yaparken PowerPoint'i görüyor olacaksınız.
Tamam, açtım hocam.
Olsun,
özür dilerim.
değil.
Çok sağ olun.
Okay, nice. Yes, already.
Hello everyone. My name is Hicret Hopoğlu. I am a PhD student at Sivas Cumhuriyet University. My supervisor is Professor Dr. Ebru Şenadım Tüzemen. Title of my presentation is Dependence of Film thicknesses on the XRD, EFM, and transmittance properties of nickel oxide. This study was supported by the scientific research project unit of Sivas Cumhuriyet University as a graduate thesis with project number F1991 640. Contents, introduction, experimental details, structure properties, optical properties, results. Introduction, compounds formed by metals reacting with oxygen are called metal oxides. Metal oxide thin films are materials with wide application area. The benefit of using metal oxide is that their chemical and optical electronic properties can be tuned to allow charge exchange with a wide variety of organic molecules. Metal oxide gas sensors have attracted a lot of attention recently due to their high sensitivity, fast response, and recovery times, low power consumption, and low production costs. One of the metal oxide materials obtained from metal with these properties in nickel, which is a ferromagnetic transition metal. Nickel is oxidized to a chemical stable nickel oxide with cubic rock salt type structure, intrinsic p-type semiconductor behavior. Nickel is an easy, available, and abundant material in the world. This metal also has got conductivity only after metals such as copper, gold, silver, and platinum. Very good attention of nickel to glass results in a very smooth surface of the ground thin films. Nickel oxide, p-type oxide semiconductor, has received great attention due to its versatile and adjustable properties. It is one of the critical materials in a wide range of electronic applications. Due December, the wide energy band, December high resistivity of nickel oxide or nickel 2 oxide having a wide energy band gap of 3.6 4 electrovolt. Nickel oxide is widely used in optoelectronic and studies in p-n heteroelectronics. The properties of nickel oxide thin films largely depend on the deposition method and conditions. Experimental details. Nickel oxide thin films were coating on a glass substrate by using a 0.250-inch thin nickel oxide target with 99.900 and 99% purity and different thicknesses by RF magnetron sputtering method. Nickel oxide target material with 99.900 and 99% purity instead of nickel target directly was preferred because it enables the ground nickel oxide film to grow in a stable composition. The structure and optical properties of the films were examined and the energy band gap was calculated. In this study, nickel oxide thin films were grown by using reactive RF magnetron sputtering method with a variation of thickness 100, 150, 200, 250, 300, and 400 nanometer at room temperature. Deposition parameters for thin films as follows. Argon gas 100%, bass pressure 7.8 times 10 to the minus 6 torr, working pressure 11 times 10 to minus 3 torr, power 150 watts, rotate 10 RPM, and room temperature. Structure properties. X-ray diffraction is used to understand the structure properties of films. XRD is one of the most important characterization is semiconductor analysis because the particle size and the distance between the planes are calculated based on the half maximum width obtained. These parameters give us information about the crystal quality of the material. XRD measurements in this study were made with the device on the right. The crystal structure, lattice parameters, volume, and the 111 space of nickel oxide films on glass substrate were determined using XRD data and Rietveld refinement analysis. Figure 1, A and B show Rietveld refinement analysis of 100 nanometer and 400 nanometer nickel oxide films. Here, black circle and red line, blue line, and green bar show experimental data, simulated fit, difference, and break position of observed peaks. The inset atomic structure of nickel oxide film were obtained from foolproof software and show equal occupied nickel red and oxygen green atoms. The nickel oxide film deposition at different thicknesses of 100, 150, 200, 250, 300, and 400 nanometers at constant pressure of 11 millitorr were summarized in figure 1C. The crystallinity were improved by increasing film thicknesses from 100 nanometer to 400 nanometer, and the main peak of 111, 200, and 220 plans became more apparent. Differently, the lattice parameters and the 111 space were decreased from 4.2887 angstrom to 4.2389 angstrom, and from 2.4761 angstrom to 2.4473 angstrom respectively, due to increased pressure during nickel oxide film deposition. Rietveld refinement analysis of nickel oxide films on glass substrate were summarized in table 1 for crystal structure, lattice parameters, volume, D111 space, surface properties of EFM analysis. The surface properties of the films have an important role on their optical and electrical properties. The morphology of the films was characterized by atomic surface microscope, EFM. EFM is a method that can measure surface topography from the angstrom level to 100 microns. It can measure atomic level force with very sensitive cantilever surface scanning. EFM can be applied in many fields such as solid state physics, semiconductor technology, molecular engineering, polymer physics and chemistry, surface chemistry, molecular biology, cell biology, and natural science such as medicine. Almost spherical nickel oxide grain formation on the surface, which was uniform and homogeneous distribution. The average grain size was calculated using log normal fit and found to be 54.28 plus minus 0.33 nanometer with a narrow size distribution between 30 nanometer and 18 nanometer. Optical properties. The optical band gap of the films were calculated using the Tauk formula with the aid of the absorption curves measures with the Curie 5000 spectrophotometer. Alpha equal 1 over d ln t, where t is the transmittance of the thin film and d is the thickness of the film. The relation between the absorption coefficient and the incident photon energy and the band gap of the material is given by alpha h nu equal b h nu minus eg over n. Here h nu is the photon energy, alpha is the absorption coefficient, b is constant, and eg is the energy band gap. In this equation, it takes n equal 1 over 2 for the direct band gap and n equal 2 for the indirect band gap. In this equation, alpha depends on the film thicknesses for thin films. The variation of the transmittance of nickel oxide thin films produced on glass with different thicknesses, 100, 140, 50, 200, 250, 300, and 400 nanometers at 11 millitorr pressure according to wavelength is shown in the figure. With increasing film thicknesses, the transmittance of the films decreases due to the thickness effect. It is seen that the absorption at gate shift to a longer wavelength with increasing thicknesses, and this decrease in transmittance is thought to be due to free Curie absorption with increasing Curie density in the thicker films. The figure shown that the direct energy band gap decreased from 3.74 to 3.70 electrovolt as the film thickness increases from 200 nanometer to 300 nanometer. It also suggests that the reason for the change in the band gap is the amorphous structure of the film. Since it is not clear whether nickel oxide has a direct or indirect energy band gap in the literature, we calculated both. Energy band gap of direct and indirect energy of thin films produced in different thicknesses. Results. The crystal structure, transmittance, and energy band gap of the films were studied in detail. The energy band gap of the produced thin film materials was determined by UV Wisner-Neer spectrophotometer. With the materials realized within the scope of the study, new physical mechanisms and innovative scientific results have emerged. In this case, knowledge has been provided to the study in which special crystal planes are preferred and to the relevant groups. Thanks for listening.
Okay, thank you, Ms. Vidret. Are there any questions, dear participants? If you have a question, can you ask directly on the chat screen? No questions. Thank you again.
Thank you.
And next speaker is Yeliz Özkök. Yeliz is also my group, is also from my group, Gazi Photonik, Ankara, Turkey. Title of talk is Production and Characterization of titanium oxynitride thin films for stent applications by co-sputtering system with confocal geometry. I leave the microphone to Yeliz. Good luck.
Thank you very much.
Can you share your screen, please?
Hello everyone, I'm Yeliz Özkök. I'm a PhD student at Gazi University, Department of Physics. At the same time, I work at the Photonics Application and Research Center. This is the big development of titanium oxynitride thin films on solid and flexible substrates. My advisor, Professor Dr. Mehmet Çakmak, the presentation I have prepared prediction and characterization of dioxinate thin films for stent applications with the co-sputtering system with the confocal geometry method. Outline, why stent, material information, stent design, why titanium oxynitride, coating of titanium oxynitride thin films, characterization, results, and conclusions. Why stent? Stents are important medical devices used to improve the quality and
Sorry, Yeliz, your voice is not good, very low. Can you check it, please? No, not good. No, we cannot. Yeliz, maybe we can continue with your record, if you're okay, because there is a problem in your voice. Please, my colleague, video record for Yeliz.
Hello everyone, I'm Yeliz Özkök. I'm a PhD student at Gazi University, Department of Physics. At the same time, I work at the Photonics Application and Research Center. Thesis topic, development of titanium oxynitride thin films on solid and flexible substrates. My advisor, Professor Dr. Mehmet Çakmak. Presentation I have prepared prediction and characterization of titanium oxynitride thin films for stent applications with the co-sputtering system with the confocal geometry method. Outline, why stent, material information, stent design, why titanium oxynitride, coating of titanium oxynitride thin films, characterization, results and conclusions. Why stent? Stents are important medical devices used to improve the quality and life expectancy of patients all over the world due to leading causes of death such as heart disease and stroke. Coronary artery disease is characterized by arterial narrowing due to fat deposits under the endothelium that restricts blood flow. Starting strategy aimed at restoring normal blood flow involves the placement of special devices stents into the narrowed vessel using fluoroscopic and/or endoscopic guidance. Slow radial self-expansion of the stent or use of a balloon catheter results in a stable position within the vessel, which allows the anatomical form and size of the vessel to be restored, thereby normalizing blood flow. Despite the promising results of stenting technology and implantation, removing the vessel inside of an implanted stent is still a serious problem. To overcome this fundamental problem and obtain blood and tissue compatibility of the stent, surfaces must be achieved. One of the current solutions to this problem is to adapt to known coating with the most suitable properties to replace bad stent surfaces. The located prosthetic coating based on dioxin on a steel stent. Various inorganic materials are available for improving the surface properties of the implant material in medical applications. During the production of stent coatings, possible inorganic materials and nitrites, oxides, carbide, and silicate, hydroxy-based materials, noble metals, diamond and carbon. Material information. The first materials used for stents were metals such as stainless steel, tantalum, nitinol, a nickel-titanium alloy, and a cobalt-chromium alloy. Stainless steel offers resistance, hardness, and good protection against corrosion, but biocompatibility is limited. Nitinol is an alloy that has proven to have good biocompatibility, but there are risks associated with nickel migration from the material leading to an immune response issue. In practice, there is no difference between stainless steel and tantalum in reducing the rate of thrombosis. Among commercially available stents, the risk of blood loss and coronary remodeling is lowest for products coated with thymoxinitrides, and the manufacturability quality price ratio looks very promising. Titanium is a widely used material for medical devices due to its inerts and high biocompatibility compared to other metals, including stainless steel. Stent design. In this study, we designed our own stent using the SolidWorks program. The designed stent has an outer diameter of 4 mm and inner diameter of 3.50 mm, a wall thickness of 0.25 mm, and a length of 40 mm. White thymoxinitride. The need for thymoxinitride coatings is due to the high incidence of instant restenosis of heavy metal stents and increased risk of life-threatening late thrombosis after implantation of drug-eluting stents. As an alternative to bare metal stents and drug-eluting stents, thymoxinitride coating stents quality new generation biological active stents have been developed. Stymox nitrate coated stents show good results in mass flows, stenosis and target vascularization, as well as reduced fibrinogen binding and platelet adhesion. It is also known to reduce migration, toxicity, and inflammation of nickel, chromium, molybdenum, or other metals from the stainless steel surface. In these coatings, titanium improves biocompatibility if inert and has excellent corrosion resistance. Styrene oxide improves stent compatibility with blood and living cells, while the presence of nitrogen in the structure reduces platelet adhesion and fibrinogen binding. There is a mechanical problem for thinner coatings based on Stymox nitrate. Thicker films are more biocompatible but have worse adhesion to the substrate. This leads to defects in the coating and impairs both fluid and tissue compatibility. The amount of oxygen and nitrogen in the equivalent affects the surface topography, morphology, as well as mechanical and biocompatibility properties, hence become less thrombogenic with increasing nitrogen content. Reduce platelet and fibrin deposition, reduce inflammation, injuries, and bronchial, minimizes thrombus formation. Coating of dioxanidin films, sputtering technique. It is the process of depositing atomic spatials on the substrate by spraying from the target surface with the generated plasma. In this study, before the dioxanid coating was applied on the stent, calibration samples of the CO sputtering system with the confocal geometry method were drawn. 16 stainless steel sublime glass and crushed silicon were chosen as substrates. Styrene nitrate was used as the target material. The coatings carried out at room temperature had an argon ratio of 100% and an argon pressure of 3 mV. Characterization. Morphological properties of Stymox nitrate thin films were investigated by XPS, AFM, and SIMS techniques respectively. X-ray photoelectron spectroscopy. XPS analysis of dioxanid thin films coated on silicon and stainless steel substrates were performed. In the analysis, results obtained for silicon, the O1 ratio was 33.27. The C1 ratio was 41.50. The N1 ratio was 11.99 and the T2E ratio was 13.24. The T2P peak at 465 electron volt represent the dioxanid thin film. In the analysis, results obtained for stainless steel, the O1 ratio was 36 or 36.45 the C1's ratio was 28.67 the M was ratio was 18.39 and the T2P ratio was 16.48. T2P peaked at 455.833 electron-volt velocity dioxide temperature. Atomic force microscopy. AFM analysis of thin films grown on stainless steel and silicon substrates was performed. For stainless steel, 2D and 3D images were obtained in a 20 by 20 square micrometers scan area. The RMS value was found to be 37.71 nanometers. For silicons, 2D and 3D images were obtained in 3 by 3 square micrometers scanning area. The RMS value was found to be 1.07 nanometers. Secondary ion beam spectroscopy. In addition, the distribution of mixed species TNOC was observed with the secondary ion mass spectrometry, depth profile, and target thickness value of approximately 239 nanometers was observed. Result and conclusions. Prediction and characterization of dioxide pollutants following generation bioactive stand was carried out. Oxygen was observed in the structure event of the argon ratio of the films produced using the sputtering method with biometer was 100%. In many studies, substrate bias voltage and substrate temperature are applied. However, neither was applied in this study. XPS measurements showed that both polysilicon and 316 and stainless steel samples contain nitrogen in their structure. In the analysis, results obtained for silicons the target thickness approximately 230 nanometers was reached in 6 measurements. Since stainless steel samples have larger particles in AFM measurements, pure silicon samples were analyzed in a wider scanning area, 20 by 20 square micrometers and 3 by 3 square micrometers scanning area. RMS values were obtained as 37.71 nanometers and 1.07 nanometers respectively. In the future, it is aimed towards the projection. The processing stand be designed on 316 arsenal heap and to coat it with a dioxide tint. Thank you for your attention.
I am here. Thank you, Yeliz. We are so sorry for that. Our young researcher wants to present it, but it was such a problem. Sorry, we couldn't upset her, of course. Next speaker is Volkan Bozkuş from Department of Photonics, İzmir Institute of Technology, Turkey. His title of talk, Tuning and the electroluminescence properties of blue polymer light emitting diodes by incorporation of parallel d-emit derivatives. Please, are you okay?
Can you hear me?
Yes, we can hear, but
I think the camera doesn't work.
That's not good, your voice.
It's okay. Can you hear my voice clearly?
Now is okay.
Okay. I trying to open the camera.
Okay. And please, you can share your screen.
Okay. Can you see my screen now?
No, not yet. Yes, okay. Can you open the full screen if it is possible?
Yes. But I think again the camera doesn't work.
We see your screen.
Okay.
No, it's good.
Sorry for the camera.
But end of the
yes,
your presentation, it's okay.
Is it okay now?
Yes, very good. Okay.
Thank you very much. My name is Volkan Bozkuş from İzmir Institute of Technology, Department of Photonics. And today I will share my organic light emitting diodes results. First of all, here's the outline. And first of all, I will give you brief information about the organic light emitting diodes and its challenges, and then I will continue with the some literature review, and then I will inform you about the experimental process, and after that I will share my results and I will discuss about, and I will finish with a conclusion. Organic light emitting diodes, in their simplest definition, they are coated by the organic light emitting material is coated between the two electrodes, and there are sometimes electron transport layer and hole transport layer is used for increase the device performance. And organic light emitting diodes have been frequently used in solid state lighting and display technology in recent years due to their outstanding features like contrast ratio, resolution, viewing angle, and also they can be flexible display, and they are very thin compared to LED TVs. But there is some disadvantage. For example, they are expensive, and durability of OLEDs are issue. And the main challenges, the biggest challenges of organic light emitting diode is the emission from the blue region is much lower compared to the red and green emitting material. And the several reason there is a several reason for this, and because the blue part of because blue emission material have higher energy gap, so this energy gap face some difficulties in charge injection, and also they are long external lifetime, which makes the emission losses through the charge or energy transfer, and also they have lower lateral time compared to red and green emitting material. In our study, we focused the blue emitting polymer material like PFO post material, as you can see here. There is a lot of articles placed in the literature. The first one is here. They used PFO post as a blue emitting material, and they added two different orange red material to the PFO material as a blend, and they obtained white light emission, and blue part is belong to PFO post material. And also there is some other approach to use PFO material. They can be used as a host material. In this article, they get the electroluminescence from parallel derivatives by using PFO as a host material, and also PFO emission can be manipulated by differentiation the annihilation temperature and also time. In this work, they increased it, they changed the annihilation temperature and obtained different electroluminescence properties. They observed both blue light and the green emission light from the PFO post. But in our study, we focused to enhance the blue emission from the PFO post material by doping the parallel diamides, two different parallel diamides. The one is very well known in the literature, the parallel diamide reference, we call it, which doesn't contain any Bay functionalization at this exposition, and the other is synthesized in our laboratory, which contains the acetyl-Brigitte trisopropyl acetylene group in the Bay position in that exposition. And also we also used two different type of whole transport layers, which one is the PVK material and other is the PVK MCP blend material. And we fabricated 7 different device structures in here, and we found that electron mobilities of the parallel derivatives is quite high to compare with the general organic materials. and the electron mobilities of the parallel derivatives is high, and we will use this electron mobility to enhance the charge balance at the active layer. And here's the results. If you look at this chart, you will see in the presence of the whole transport material as PVK, MCP, and bare PVK. You will see in the presence of the whole transport layer, the turn-on voltage is slightly increasing, and despite the increasing in whole mobilities from PVK to MCP, the current also decreasing, and highest current at the same voltage belongs to reference 1 device, and which doesn't contain any whole transport material, and it is understood from the luminescence properties and also the relative external quantum efficiency. The reference 3 is worked better when we compare it with the others, and it is understood that the recombination is low for the reference 1, and possible and because of the possible electron leakage and the poor electron hole imbalance in the active layer is possible for PDI, for reference 1 device, and highest electroluminescence is and highest efficiency is obtained when we use the PVK as a whole transport material. But when we add the PDI derivatives, PDI ref and PDI1, the situation is reversed. I try to open the camera, but can you hear me?
Yes.
What happened? Sorry for that. I tried to share. Can you see the screen?
I don't know any idea. No, we cannot see your. Yes. That's already. Okay, we can see now.
Sorry for that. If I conclude in this situation, we observe the higher electroluminescence and the high external quantum efficiency is belong to PVK whole transport material. But when we add the PDI1 and PDI reference to the PFO post material, the situation is changed. In this the situation is reversed, and PDI derivatives exhibit higher luminescence despite drawing the less current, which can be explained by the electron and hole balance. In the here, as you can see here, the D3, which contains the PVK MCP, is the lowest. Sorry, yes, is around the terminal voltage is around 5 voltage, and increase, and the luminescence is much more higher compared to other materials. And in this situation, the PVK MCP whole transport material is worked better compared with the PVK the bare PVK whole transport material here, and we found that the addition of the parallel derivatives is increased the electron mobilities in the active layers because of the high n-type properties of the parallel derivatives in here. And if we talk about the electroluminescence features and the electroluminescence features of the REF1, REF2, and REF3, we observed with a one intense peak at the 421 nanometer, and this shape of the spectrum is compatible with the literature. And there is also the minor peaks at the 442 nanometer and 472 nanometers. But if we add the parallel PDRF and PDI1, this minor peaks is increased much higher, and also this increasement is not caused by the cathode effect of the PFO pulse. This article is placed in the literature. They observed the cathode effect of the PFO pulse, and they obtained the electroluminescence at the green region. But there is a minor peak existing in this spectrum. When we compare our results and this cathode effect emissions spectrum, we can say that our electroluminescence is not originated from the cathode effect, but originated from the increasement exton density at that minor peaks, and because of the low energy band gap of the parallel derivatives and the high electron mobilities is the reason why this this is the reason why this pitch is increased for the PDI for the adding the PDI derivatives, because the PDI derivatives is enhancing the electron mobilities from PDI derivatives to the PPA post at the lower energy levels in here. This table is summarized of the all fabricated device, and we found that PDI ref including device has much higher external quantum efficiency, the relative external quantum efficiency, and the luminescence. But but there is some shift in the CII coordinates. In the deep, the CII coordinates shifting from deep blue emission to the blue emission, and also the full theta maximum is also increasing. Also the full theta maximum is increasing, which can be used as a white light emitting device, so which covers the entire blue region. And here's the conclusion. We tried two different whole transport material in the whole transport layer, and we obtained that without using parallel limit derivatives, the PVK the bare PVK PVK whole transport material is worked better. but when we use when we add the high electron mobilities n-type Perlen derivatives to the PFE post to the active layer, the PVK-MCP, which PVK-MCP is a higher Hall mobilities compared to the bare PVK. The PVK-MCP is worked better compared to the just PVK. And we also obtained the different electroluminescence properties by doping the PDI derivatives to the active layer. And also we observed the increased H-stone recombination density, H-stone recombination at the lower density of state of the PFO post material, and because of the increasement at the lower energy density, lower energy state, the performance is increased. And I would like to thank to my research group members and the organizing committee for giving us this opportunity, and to the TÜBİTAK support funds. And I would like to thank all of you to attention. Thank you very much.
Okay, thank you very much for your nice presentation, dear Volkan. Are there any questions, dear participants? I'm waiting. Check the screen. No questions. Thank you again.
Thank you very much.
I would like to invite last speaker, Lala Gahramanli. Sorry for my pronunciation. Lala from Bakü State University, Azerbaijan. The title of talk: Influence of Environment to Optical Properties of Cadmium Selant Nanoparticles. Are you here? Can you hear me? Okay. Please, can you share your presentation and open your voice, please? And also, is possible, your video?
Hi, everyone. Can you hear me?
Yes, yes, it's good.
Okay, I greet all conference participants. I am Lala Gahramanlı from Bakü State University. My title is about influence of environment to optical properties of cadmium as nanoparticles. My speech will consist of several parts. The first of these, electron-ion interaction and potential energy. Then experimental part, in this experiment modeling part, and result and discussion. In this study, the purpose is to investigate the effect of electrolyte solution on the optical properties of cadmium S nanoparticles obtained by sonochemical method. To determine the effect of different ambience, obtained sample were analyzed how vary the band gap at different concentration within different electrolyte solution. In here, we use 3 different ambience, such as cadmium nitrate tetrahydrate, cadmium acetate dehydrate, and sodium chloride water solution in different concentration as an electrolyte solution. The energy spectrum of the all samples changed when the sample was placed in different ambience, and we would like to determine this effect. First of all, I would like to speak about the electron-ion interaction and potential energy. The nanoparticles can be interaction with each other and the environment by different forces, such as electron-ion interaction, dipole-dipole interaction, and ion-electron interaction. And the equation of this force interaction, as shown here. If we insert the nanoparticle in an ambient solution, the interaction occurs between ambience and carriers. The movement of carriers is described by Schrödinger equation and described as follow. In here, we notate the all the consist of units. And if we insert the sample in the ambient with a certain dipole moment, the potential energy will change and the Schrödinger equation will be described as follow. Then I would like to speak our main experimental part, cadmium S. Semiconductor nanomaterials have attached much interest due to interesting physical and chemical properties. These materials show unique properties compared with their bulk materials due to nanoscale size. Due to nanoscales of particle, quantum size effects are also observed in them. They have size-dependent optical and electronical properties. Due to quantum size effect, cadmium sulfate is an important direct intermediate band gap, which is equal to 2.42 electron volt at 300 Kelvin, with excellent thermal and chemical stability and strong optical absorption, and is used in solar cells, photodetectors, light emitting diodes, and laser, and so on. In this experiment, cadmium S nanoparticle were obtained by sonochemical method, which is shown in here, our experimental part. Then we were investigated by X-ray diffraction method, and to determine the size of particle by scanning electron microscopy, and to determine the optical properties, and from this result to determine the band gap value of this sample, we use ultraviolet visible spectra. From the result, we can show that in here, the structure of these materials, and we can show that the obtained sample were mixed phase, such as cubic and hexagonal phase. From some results, we can say that the particle size is between the range of 70 and 33 nanometer, and from UV spectroscopy, we can say that the pure cadmium S nanoparticle band gap is 2.51 electron volt. So I would like to speak about our experimental part. We obtained the cadmium S nanoparticle by sonochemical method. So we want to determine how affect the electrolyte solution to these pure cadmium S nanoparticles. For this purpose, the obtained nanoparticles were placed in different ambient solution, such as cadmium nitrate, cadmium acetate hydrate, and sodium chloride, and all these three different ambience in different concentration, 4 different concentration. So in here we use 3 concentration of this sample as shown in the picture. So this is our modeling. This is our modeling. This is the electrical double layer. The electrical double layer interact with the nanoparticles and with a different ambient solution, or it may be other ambience or other environment, and etc. So in here you can see the thickness of the double electrical layer. In here we noted the equation. So you can see X-ray diffraction. This diffraction is about the cadmium S nanoparticles, pure cadmium S nanoparticles, and cadmium S adding to all three ambient solution before and after X-ray diffraction. In here, we can say that the structure had an effect on the bandgap value of sample, and in here there is not any changing of phase. It was determined that there was no change in the structure from the obtained X-ray spectrum. So in here you can see the transmittance spectra, all three electronic solution of 4 concentration. So in here we can we use this transmittance spectra and we can obtain the bandgap value of this sample. So we made this such as table, and in table, from the table, the bandgap of nanoparticles strongly, we can say that the nanoparticles strongly depend on the nature of environment. Adding cadmium S into cadmium acetate solution, the bandgap decreases slightly by increasing of concentration of electrolyte solution. Cadmium S, bandgap of cadmium S in cadmium nitrate and sodium chloride solution were decreased slightly. It is explained by the solubility of cadmium S in different electrolyte solution as shown. As can be seen from as an increase in the concentration of solution, the bandgap decrease. The nature of the change also depends on the anionic component of this selected electrolyte solution. With increasing concentration, the ion density on the near surface region of the particle change. In addition, this leads to a change in the potential energy of charge carrier in nanoparticles. So a change in potential leads to change in the energy spectrum of charge carriers. As shown, the measurement result in same case. The bandgap becomes smaller than that of bulk structure, approximately 2.42 electron volt. A change in the nature of energy spectrum leads to change in the different effective mass of charge carrier. So experiments show that the bandgap value can sometimes be less than the size of the bulk crystal. This is due to the fact that the nanoparticles have defect structure and the effective potential varies depending on the environment of the surface. So this leads to change in the effective mass. Thus, it leads to change of bandgap of value. As conclusion, we can say that the studies have shown that the bandgap of nanoparticles depend on the type of environment. So we can see that the bandgap can be changed from 2.25 electron volt to 4.13 electron volt. This change can be controlled by the changing of concentration of different electrolyte solution. So this change is due to the fact the potential energy of charge carrier in nanoparticle depending from ion and electron interaction. Thanks for your attention.